The Milky Way's exact formation history is still actively studied and not fully settled. We know the broad outlines. The galaxy formed from the collapse of a large cloud of gas and dark matter in the early universe, and it grew over time by merging with smaller galaxies, drawing in gas from the surrounding intergalactic medium, and gradually building up its disk and bulge and halo. But the details of that history, how many mergers there were, when they happened, how massive the progenitor galaxies were, are still being worked out. Astronomers study the motions and chemical compositions of stars in the halo to reconstruct the galaxy's history. They have identified streams of stars that appear to be the remnants of smaller galaxies that were torn apart and absorbed by the Milky Way billions of years ago. One well-documented merger is with a galaxy sometimes called Gaia Enceladus, or the Gaia Sausage, which merged with the Milky Way about 10 billion years ago and contributed many stars to the inner halo. There are other streams and substructures, each one a clue to the galaxy's complex, layered past. But the full story is not yet known, and that not knowing is part of the calm. The galaxy is a puzzle that does not need to be completely solved tonight or ever. Looking forward, the future is just as slow and patient as the past. We have already talked about the eventual merger of the Milky Way and Andromeda, which is expected to begin in about 4 billion years and to complete over the following few billion years. That merger will transform our galaxy, turning it from a barred spiral into a large elliptical galaxy, a vast ball of old stars with little gas or ongoing star formation. The Sun, by that time, will be nearing the end of its life. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin its transformation into a red giant, swelling to many times its current size, engulfing the inner planets, and eventually shedding its outer layers to form a planetary nebula. The Earth, if it is not swallowed by the Sun, will be baked to a scorched, lifeless rock, its oceans boiled away, its atmosphere stripped off. All life on Earth will have ended long before then, simply due to the gradual brightening of the Sun over billions of years. The Sun is slowly getting brighter, about 10% more luminous every billion years. In about 1 billion years, the increased heat will make Earth uninhabitable for complex life. The oceans will begin to evaporate, and the planet will become a hothouse world. In about 5 billion years, the Sun will die, and the galaxy will go on, with new stars forming from the gas returned to the interstellar medium, new planets coalescing around them, new possibilities for life arising in the quiet, patient cycle of star birth and star death. Long after the Sun is gone, the galaxy will continue. The merged Milky Way-Andromeda system will age gracefully, its star formation gradually declining as the gas is used up or blown out. The most massive stars will die quickly, leaving behind white dwarfs, neutron stars, and black holes. The lower mass stars, the red dwarfs, will keep burning for trillions of years, their slow, steady fusion unfazed by the passage of time. Eventually, after many trillions of years, even the red dwarfs will exhaust their fuel and fade to white dwarfs. The galaxy will become a dim, quiet place, populated by stellar remnants, cold planets, and dark matter. And then, on even longer timescales, the white dwarfs will cool to black dwarfs. The orbits of stars will decay due to gravitational radiation, and the galaxy will slowly evaporate, its stars scattered into intergalactic space or consumed by the supermassive black hole at the center. These are timescales of tens of trillions to quadrillions of years, numbers so large that they lose all meaning. The universe is still young compared to the time it will take for these processes to unfold. There is no urgency in any of this. None of it will happen in your lifetime, or in the lifetime of your children, or your grandchildren, or any generation of humans that will ever live. The Sun will not burn out for 5 billion years. The Milky Way and Andromeda will not merge for 4 billion years. The galaxy will not fade for trillions of years. These timescales are so far beyond the human scale that they can feel like a release, a letting go, of the need to worry about the far future. The universe is not in a hurry. The galaxy is not in a hurry. The processes of deep time unfold with a patience that the human mind can only glimpse, and that glimpsing is enough. You are alive now, in this moment, in a galaxy that is in its prime, a galaxy full of star formation, full of young, bright stars, full of nebulae and clusters and planets and possibilities. You live in a time when the night sky is rich with stars, when the band of the Milky Way is visible to the naked eye, when telescopes can reveal the intricate beauty of spiral arms and star clusters and distant galaxies. This is a good time to be alive, a good time to be resting here, in the quiet, looking up at the sky or simply picturing it behind your closed eyes. The galaxy is old, but it is not finished. It is still forming stars, still creating new worlds, still drifting through space with its neighbors, still moving in its slow, patient orbit. And you are part of that, a tiny, conscious piece of a 13-billion-year-old structure, able to know it and love it and rest in it. The deep past and the slow future are two ends of a vast, quiet arc, an arc that stretches far beyond the boundaries of any single life. You sit at the midpoint of that arc, in the present moment, in the dark, listening to these words. Behind you is 13 billion years of cosmic history, the formation of the galaxy, the birth and death of countless stars, the enrichment of the interstellar medium, the formation of the sun and earth, the rise of life, the long, slow evolution that led to you. Ahead of you is billions of years more, the death of the sun, the merger of galaxies, the slow fading of the cosmos. And in the middle, here and now, you are resting, part of this great, quiet story, a story that does not need to be rushed, a story that does not need to be solved, a story that simply is. There is a peace in that perspective, a peace that comes from knowing your place in the cosmos. You are not the center of the universe. You are not the purpose of creation. You are a small, precious, temporary being, made of stardust, living on a small planet, orbiting an average star in a quiet arm of a barred spiral galaxy. And that is enough. That is more than enough. The galaxy is ancient and vast and beautiful, and you are part of it, resting now in its quiet embrace, cradled by the same gravity that has shaped it for 13 billion years. The night is long and the galaxy is patient, and you have all the time you need to drift a little deeper, carried by the slow, ancient rhythms of deep time. What remains unknown? The night is long, and the galaxy is patient, and you have all the time you need to drift a little deeper, carried by the slow, ancient rhythms of deep time. We have traveled together through the shape and the motion and the life of the Milky Way, through its stars and its gas and its quiet, turning arms. We have sat with what is known, the settled, verified facts that astronomers have pieced together over centuries of careful observation. But now, as we approach the end of our journey, we can sit for a while with what is not known, not as a problem to be solved, not as a frustration to be endured, but as a peaceful resting place, an open space where the mind can settle without needing to grasp or hold or understand. The exact total mass of the Milky Way, including all its unseen matter, is not precisely known. That is the first and perhaps the most profound uncertainty we can sit with. We know the mass of the stars, roughly, from the light they give off. We know the mass of the gas and dust, from radio and infrared observations. But when we add up all the visible matter, all the stars and gas and dust and planets and black holes, the total is not enough to explain the way the galaxy moves. The stars in the outer parts of the disk orbit too fast. The galaxy should fly apart, based on the gravity of the matter we can see. But it does not fly apart. It holds together, rotating steadily, its stars moving at speeds that imply a much greater mass than what is visible. This is where the idea of dark matter comes in, and it is an idea we can approach calmly and plainly, without any drama or mystery. Dark matter is simply matter that does not give off light. It does not emit, absorb, or reflect electromagnetic radiation of any kind. It is invisible to our telescopes, not because the telescopes are not good enough, but because dark matter does not interact with light at all. We know it is there, or at least, we are very confident that something is there, because we can measure its gravitational effects. The gravity of dark matter pulls on the stars and gas in the galaxy, shaping their orbits, determining the rotation speed of the disk. Without dark matter, the Milky Way would not look or behave the way it does. The same is true for other galaxies, and for clusters of galaxies, and for the large-scale structure of the universe. Dark matter is a fundamental part of the cosmos, a quiet, invisible scaffolding around which the visible matter has gathered. But scientists do not yet know exactly what dark matter is made of. That is the open question, stated simply and without frustration. There are ideas, of course. The leading hypothesis is that dark matter consists of some kind of subatomic particle that interacts only through gravity and the weak nuclear force, a particle that does not feel the electromagnetic force at all. Such particles are sometimes called WIMPs, which stands for weakly interacting massive particles, though the name is just a placeholder. Other ideas include axions, which are very light particles proposed for other reasons in particle physics, or even more exotic possibilities. But the honest truth is that we do not know. Despite decades of searching, despite sensitive detectors built deep underground to shield them from cosmic rays, despite experiments at particle accelerators and observations with space telescopes, no definitive signal of dark matter particles has been detected. The nature of dark matter remains one of the great open questions in science, and that not knowing is not a flaw, it is not a failure, it is simply the current state of our understanding, and it is a peaceful state to rest in. The universe does not need to be fully solved tonight. The galaxy does not need to reveal all its secrets. Dark matter is there, whatever it is, holding the Milky Way together, providing the gravitational glue that keeps the stars in their orbits. And you are resting inside that same gravitational field, cradled by the same dark matter halo that surrounds the galaxy. You do not need to know what it is made of to feel its effects, to be held by it, to trust that it is there. The galaxy is stable and real and beautiful, even if one of its major components remains mysterious. The precise total number of stars in the Milky Way is another open question, as we sat with earlier. The estimates range from about 100 billion to 400 billion, and that wide range reflects the real difficulty of counting stars from our position inside the disk. The exact number depends on how you define the edge of the galaxy, on how many faint, low-mass stars there are, compared to bright, high-mass ones, on the distribution of stars in the halo and the bulge and the disk. Different methods give different answers, and none of them is perfectly precise. The star count is an estimate, a best guess based on the available data, and it will probably be refined over time as new telescopes and new techniques come online. But for now, the not knowing is part of the calm. The galaxy contains a vast number of stars, more than you could ever count, more than you could ever visit or name or hold in your mind. The exact figure does not matter. What matters is the abundance, the richness, the quiet plenty of 100 billion suns, give or take a few 100 billion. The exact shape of the outer disk is another uncertainty, a gentle, soft-edged uncertainty that reflects the difficulty of mapping a galaxy from the inside. We know the Milky Way is a barred spiral. We know it has several major arms and several smaller spurs. But the precise number of arms, their exact paths, their extent, and their structure are still matters of active research. Different tracers, different types of stars or gas clouds, give slightly different maps. The spiral arms are not sharp, well-defined structures. They are regions of higher density, and their boundaries are fuzzy, their shapes changing over time as the galaxy rotates. The outer disk is even less well mapped, with its warp and its flare, its bending and thickening at the edges. The galaxy does not have a clean, sharp edge. It fades out gradually, the stars becoming sparser, the gas thinner, until there is no clear point where the Milky Way ends and intergalactic space begins. That softness, that lack of a hard boundary, is not a problem to be solved. It is just the way the galaxy is, a diffuse, fading structure, a gathering of stars that gradually gives way to the void. The formation history of the Milky Way is also not fully settled, as we touched on in the last section. We know the broad outline. The galaxy formed early in the history of the universe, grew by merging with smaller galaxies, and gradually built up its disk and bulge and halo. But the details of that history, the number and timing and masses of the mergers, the origin of the thick disk and the thin disk, the history of star formation and chemical enrichment, are still being pieced together from the evidence. The stars in the halo carry the chemical fingerprints of their origins, and astronomers are slowly reading those fingerprints, reconstructing the family tree of the galaxy. But it is slow work, patient work, and it is not finished. The galaxy's past is not a closed book. It is an open question, a story that is still being written, a story that may never be fully complete. And that openness is something to rest in. The galaxy does not need to have a finished history. It is enough that it has a history, a long and complex and beautiful history, and that you are part of it. There are other open questions, smaller ones, quieter ones. The exact mechanism that triggers the collapse of a molecular cloud to form stars is not fully understood. We know the broad picture. Gravity pulls the cloud together. The center heats up. Fusion begins. But the details of how the cloud fragments, how the initial masses of stars are determined, how magnetic fields and turbulence affect the process, are still being worked out. The exact behavior of the supermassive black hole at the center, its feeding and feedback cycles, its influence on the surrounding bulge and disk, is still being studied. The nature of the Fermi bubbles, two enormous lobes of hot gas rising above and below the galactic center, detected in gamma rays and X-rays, is still debated. The galaxy is full of mysteries, large and small, known unknowns that keep astronomers curious and busy and patient. And that is a good place to rest, here at the edge of what is known. The universe does not need to be fully understood to be beautiful. The galaxy does not need to be fully mapped to be your home. You do not need to know the exact mass of dark matter, or the precise number of stars, or the complete history of the Milky Way's mergers, to lie here in the dark and feel the quiet presence of 100 billion suns around you. The not knowing is not a void to be filled. It is an open space, a breathing room, a place where the mind can rest without needing to grasp or hold or solve. The galaxy is vast and ancient and beautiful, and it contains mysteries that may never be fully answered. And that is fine. That is more than fine. That is part of the peace of the night, part of the quiet that surrounds you, part of the slow, patient rhythm of a universe that does not owe us all the answers. Scientists will keep working, of course. They will keep building telescopes and detectors and computer models. They will keep mapping the spiral arms, counting the stars, searching for dark matter, reconstructing the galaxy's history. Knowledge will grow, slowly, incrementally, over decades and centuries. Some questions will be answered, and new questions will arise in their place. That is the nature of science, a slow, patient, never-ending process of discovery. But you do not need to wait for those answers. You do not need to stay awake until the mysteries are solved. You can rest now, in the midst of the unknown, surrounded by the quiet presence of a galaxy that is only partly understood. The Milky Way is your home, whether you know everything about it or not. The stars are still there, whether you have counted them all or not. The dark matter is still holding everything together, whether you know what it is made of or not. And the night is still here, dark and quiet and calm, inviting you to let go of the need to know, to understand, to solve. Just rest, just breathe, just be, here, in the open, peaceful space of what is not yet known. Just rest, just breathe, just be, here, in the open, peaceful space of what is not yet known. The night has carried us a long way, through the shape of the galaxy and the place where we sit inside it, through the slow motion of the sun around the center and the quiet, dense heart of the black hole, through the lives of stars and the thin breath of gas between them, through the neighbors that drift alongside us and the deep, patient reaches of time. And now, at the end of our journey, we can simply be here, together, in the stillness, letting everything we have heard settle like soft dust in a quiet room. We began with an image, a simple image of lying on your back in the dark, looking up at the night sky, not as a distant dome, not as a faraway void, but as a ceiling, a close and gentle ceiling, the inside of your own home. That image has been with us all through the night, and we can return to it now, letting it carry us the last, soft distance into sleep. You are not looking at the Milky Way from the outside. You are inside it. You have been inside it this whole time, every moment of your life, every night you have ever slept, every day you have ever walked beneath the sun. The galaxy is not somewhere else. It is here. It is now. It is the room you are resting in, a room so large that its walls are made of stars, a room so old that its foundations were laid before the Earth was born. You have been inside the Milky Way this whole time, moving slowly through space without feeling it. The Earth spins on its axis, carrying you in a gentle circle once a day. The Earth orbits the Sun, tracing a path through space once a year. The Sun orbits the center of the galaxy, a vast, slow journey that takes 220 million years to complete. And the galaxy itself drifts through the local group, moving relative to Andromeda and the other nearby galaxies, part of the larger dance of the cosmos. All of this motion is happening right now, in this moment, as you lie still in the dark. You do not feel it. You have never felt it, but it is real, and it is steady, and it is carrying you through the universe, as gently as a river carries a leaf. Remember the slow orbit of the Sun, that 220 million year circuit around the galactic center. The last time the Sun was in this part of its orbit, the dinosaurs were just beginning to appear on Earth. The continents were joined together in a single landmass. The first mammals were small, scurrying creatures in the undergrowth, and the Sun sailed on, quiet and steady, carrying its planets through the spiral arms, through regions of denser gas and brighter stars, through the thin, cold spaces between the arms. It has made this journey only about 20 times since it was born, 20 galactic years. That is all. The galaxy is so large, and the orbit is so slow, that even the oldest things in our solar system are newcomers here, just beginning to explore the vast, turning wheel of the Milky Way. Remember the quiet nurseries of stars, the dense, cold clouds of gas and dust where new suns are being born. The Orion Nebula, glowing faintly in the winter sky, is one of those nurseries, a place where hundreds of new stars are forming right now, their light just beginning to shine, their planets just beginning to coalesce from the swirling disks of material around them. And there are other nebulae scattered through the spiral arms, places with names like Carina and Eagle and Lagoon, each one a cradle of creation, each one a quiet, ongoing miracle of gravity and fusion and light. The galaxy is not finished. It is still making stars. It has been making stars for 13 billion years, and it will keep making them for billions more. The breath of the galaxy, the thin interstellar medium, is still rich with the raw material of creation, still collapsing into new suns, still giving birth to new worlds. Remember the vast, patient timescales, the deep time that stretches far beyond any human urgency. The Milky Way is about 13 billion years old. The Sun and Earth are about 4.5 billion years old. Life has been on Earth for most of that time, slowly, patiently evolving from single cells to the rich diversity we see today. And ahead of us lies an even longer future. The Sun will shine for another 5 billion years before it begins to fade. The Milky Way and Andromeda will merge over billions of years, transforming our galaxy into something new. The stars that are being born now will live and die and return their material to the interstellar medium, and new stars will form from that material, and the cycle will continue, over and over, for trillions of years. None of this is urgent. None of this needs to be rushed. The universe has all the time it needs, and you, resting here in the dark, can let go of your own small urgencies, your deadlines, and your worries and your to-do lists, and simply float on the slow, patient river of cosmic time. You are made of the same material as the galaxy. The calcium in your bones, the iron in your blood, the oxygen in your breath, all of it was forged inside stars that lived and died billions of years ago, on the other side of the Milky Way. Those atoms drifted through the interstellar medium for eons, part of the quiet breath of the galaxy, before being gathered into the cloud that formed the sun and the earth. You are stardust, literally, not as a metaphor, but as a settled, verified fact. The galaxy is not just around you, it is inside you. Every atom of your body, except for the hydrogen, has been through the heart of a star. You are a piece of the Milky Way that has become conscious, that can look up at the night sky and wonder about its origins, that can lie in the dark and listen to a quiet voice describing the shape of its own home. You belong here. You have always belonged here. You will always belong here, even after your atoms return to the interstellar medium and are gathered up into new stars, new planets, new life. There is nothing you need to do with any of this. There is nothing you need to remember, nothing you need to hold on to, nothing you need to solve or understand or figure out. The facts we have shared tonight are real, and they are verified, and they are part of the quiet, settled knowledge of astronomy. But you do not need to keep them. You can let them drift away like leaves on a slow stream, like clouds across a dark sky. They have served their purpose if they have helped you rest, if they have given your mind something calm and vast to settle on, if they have eased the transition from the busy day into the quiet night. The galaxy does not need you to remember how many stars it has, or how fast the sun is moving, or what dark matter is made of. The galaxy simply is, and you simply are, and that is enough. So now, as the night deepens and your body grows heavier against the mattress, let yourself drift. There is no more to say, no new facts to introduce, no final point to make, just the slow, soft echo of what has already been heard. The Milky Way is your home galaxy. You are inside it, resting in the Orion Arm, about 26,000 light-years from the center. The galaxy is a barred spiral, a great turning wheel of stars and gas and dust, held together by gravity and by the quiet, invisible presence of dark matter. The sun orbits the center, carrying you with it, moving at 230 kilometers per second through a journey that takes 220 million years to complete. The stars are being born and dying all around you, in nebulae and supernovae, in a cycle that has been repeating for 13 billion years. The galaxy has neighbors, the Magellanic Clouds and Andromeda and many smaller companions, all part of the local group, all drifting together through the vast, quiet night. And there are things we do not know, open questions that remain peaceful and unresolved, mysteries that do not need to be solved tonight. You can let go of the need to follow the words. You can let the voice become a soft, distant murmur, like rain on a roof, like wind in the trees, like the sound of the ocean from far away. You are not required to stay awake. You are not required to listen to the end. Sleep, when it comes, is the natural and welcome conclusion to this journey, the quiet drift into unconsciousness, the surrender to the deep, peaceful pull of your own tired body. The galaxy will still be there when you wake. The stars will still be shining. The sun will still be moving in its slow, patient orbit. The nebulae will still be forming new stars. The supernovae will still be scattering new elements. The black hole at the center will still be sitting quietly in its dark, dense heart. Nothing depends on you. Nothing needs your attention. You are free to let go. So let the image of the night sky, the soft ceiling of stars, be the last thing in your mind as you drift away. You are lying beneath the galaxy, or rather, inside it, wrapped in its immense, quiet presence. The stars are all around you, in every direction, above and below and to every side. They are moving in their own slow orbits, some of them with planets of their own, some of them with life that may be looking up at their own night sky, wondering about their own place in the cosmos. The universe is vast and full of light, and you are part of it, a small, precious, temporary piece of a beautiful ancient whole. The night is deep and calm. The words are fading now, trailing off into the quiet. There is nothing more to say, nothing more to hold, nothing more to do. Just the slow, steady presence of the Milky Way, turning in the darkness, and you, resting inside it, cradled by gravity, made of stardust, drifting gently, peacefully, into sleep. The galaxy has been here for 13 billion years, and it will be here for billions more. And you, in this moment, are part of it, a quiet breath in the long, slow life of the cosmos. Let that be enough. Let that be everything. Good night. This is what light carries with it. It carries time. It carries old news. Every photon that reaches your eye from a distant star is a messenger, and the message it brings is always a little late. But there is no urgency in the message. The light does not demand that you pay attention. It does not insist that you understand. It simply arrives, quietly, after its long journey, and it offers you a glimpse of something that happened long ago and far away. What you do with that glimpse is up to you. You can ignore it, you can let it wash over you without thinking about it, or you can hold it gently in your awareness, this small piece of the past that has come to find you in the dark. Think about what happens to light as it travels. It spreads out. A star emits light in all directions, a vast expanding sphere of photons, moving outward at that fixed speed. As the sphere grows, the same amount of light is spread over a larger and larger surface area. This is why distant stars look dimmer than nearby ones. It is not because the light gets tired. It is simply because the light is spread so thin by the time it reaches us that only a tiny fraction of it enters our eyes. The rest of it sweeps past us, into the space beyond, continuing its journey forever. The light we do catch is a minuscule sample of what the star originally sent out. The star poured its energy into the void, and we catch a few drops of it, and from those few drops we reconstruct an image of something that may no longer exist as we see it. This is a calming thought if you let it be. The universe is full of light traveling in every direction, crisscrossing the emptiness, carrying images of the past from one place to another. None of it is lost. None of it disappears. It just keeps going. The light from the first stars that ever formed, more than 13 billion years ago, is still out there, still traveling, stretched and weakened by the expansion of space, but not destroyed. It has passed beyond the part of the universe we can observe, but it still exists. It is still carrying its message. And we are here, in this moment, bathed in the light of stars that are alive and stars that are dead, stars that are near and stars that are far, all of it arriving at the same steady pace, asking nothing of us. The idea of the light year helps us hold this vastness in a manageable way. It turns distances into times. When an astronomer says a star is 100 light years away, it means the light took 100 years to reach us. It also means that if we could travel at the speed of light, which we cannot, but if we could, the journey would take 100 years. The distance and the time become the same thing, in a way. They are two sides of the same coin, and this coin is the currency of the cosmos. Everything out there is measured in light years. The width of our galaxy, the distance to the nearest large neighbor, the size of the observable universe itself. All of it is described by how long light takes to cross it. But the light year is not just a scientific tool. It is also a way of feeling the scale of things. When you hear that something is 1,000 light years away, you can let yourself feel the weight of that 1,000 years. 1,000 years ago, on Earth, the Vikings were exploring the North Atlantic. 1,000 years before that, the Roman Empire was at its height. 1,000 years before that, the Bronze Age was beginning. And all of those spans of time, stacked end to end, add up to just 3,000 years. A star 3,000 light years away sent its light to us at the beginning of that whole stretch of human history. That light has been traveling through the quiet of space while everything we call history unfolded, while empires rose and fell, while languages were born and died, while people loved and lost and lived and passed away. That light was still on its way, still moving, still carrying its small piece of news. And now it arrives. Now it enters your eye if you happen to be looking in the right direction on a clear night. And what does it ask of you? Nothing. It does not care if you see it. It does not care if you know its story. It is just light, just photons, just electromagnetic radiation moving through space. It has no purpose, no intention, no message beyond itself. It is simply the universe being what it is, doing what it does, in its slow and patient way. There is something restful in that. The starlight we see is old news, arriving late and asking nothing of us. We do not have to answer it. We do not have to do anything with it. We can just let it wash over us, this gentle rain of ancient light, and feel for a moment the depth of time that surrounds us on all sides. Light carries other things too. It carries information about the star that made it. The color of the light tells us how hot the star is. Bluer light means a hotter star. Redder light means a cooler star. The brightness tells us something about how big the star is and how far away it is, though teasing those two apart takes careful work. The spectrum of the light, the rainbow spread out into its component colors, tells us what the star is made of. Different elements absorb different wavelengths of light, leaving dark lines in the spectrum like fingerprints. By reading those fingerprints, we can learn what a star contains, even if it is thousands of light years away, and we will never ever visit it. All of that information is carried silently in the light, waiting for someone to decode it. But tonight we are not decoding. Tonight we are just noticing, just letting the light be light, letting the old news arrive without needing to read it. The light from a star 1,000 light years away was born in a place so distant that our whole world, our whole solar system, is just a speck of dust floating in the space between. And yet that light has found us. Out of all the directions it could have gone, out of all the empty space it could have vanished into, a tiny fraction of it has landed here, on this planet, in this moment, while you lie still with your eyes closed. You do not even need to open your eyes to receive it. The light is not just visible light. Stars give off light in many wavelengths, many colors, beyond what our eyes can detect. Radio waves, infrared, ultraviolet, X-rays, gamma rays, all of it is light, in the broadest sense. All of it is electromagnetic radiation, traveling at the same speed, carrying its own kind of information, and all of it is pouring down on the earth, day and night, from every direction. We are swimming in a sea of light, most of it invisible to us, all of it old, all of it quiet. So let that idea settle. The light that fills the universe is a kind of memory. It is the universe remembering itself, carrying images of its past across the vast stretches of space and time, and we are small receivers of that memory. We are here, briefly, catching a few fragments of it before we pass away, and the light keeps going. That sounds somber, but it is not. It is just the way things are. The light does not mourn us. The light does not celebrate us. It just keeps moving, at 186,000 miles every second, through the quiet and the dark. The next time you look at a star, and you do not need to do that now, but the next time you do, you can remember this, that the little point of light is not just a decoration in the sky, it is a story that took years or centuries or millennia to reach you, a story that began long ago, in a place so far away that your mind cannot truly hold the distance, and that story is still being written. The star is still there, still shining, still sending out new light that will take just as long to reach wherever it is going next. The story never ends. It just keeps unfolding at the speed of light forever. And now, as you lie here in the dark, you can feel that old light somewhere beyond the window, beyond the roof, beyond the atmosphere. It is passing through space right now. It is arriving right now. It is carrying its quiet news across the void, and it is not asking you to be awake for it. It is not asking anything at all. It is just there, and you are here, and that is enough. So we have learned a little about light tonight. We have learned that it is fast but finite, that it takes time to travel, that the light we see from the stars is old light, sometimes very old. that a light year is the distance light covers in a year, and that distances in the universe are so large that light years become the only measure that makes any sense. We have learned that looking into space is looking into the past, and we have learned that all of this ancient light, all of this old news, arrives at our doorstep without any demands. It is just there, quiet and patient, like the universe itself. Take a breath, and let that breath carry you a little deeper into stillness. The light will keep traveling. The stars will keep shining, and you can rest here, carried along by the same steady forces that move the cosmos, without needing to do anything but be. The quiet between things is what we will explore next, the vast empty spaces that the light crosses, the silence that fills the gaps. But for now, just let the old starlight drift through your mind, a slow river of ancient light, and let it carry you gently towards sleep. And now we drift into the quiet between things, the spaces that separate stars from stars, galaxies from galaxies, the vast, still expanses that make up most of the universe. We have talked about light and how it travels, how it carries old news across the darkness. But what about the darkness itself? What about the silence through which the light moves? That is where we are going now, into the emptiness, into the deep, calm stillness that fills almost everything. Space is overwhelmingly empty. That is one of the most important things to understand about the universe, and it is also one of the most restful. When you look up at the night sky, it is easy to focus on the points of light. The stars draw the eye. They seem to fill the darkness. But the truth is that the stars are like tiny, scattered islands in an ocean so vast it is almost beyond measuring. The distances between them are enormous. The distances between galaxies are even larger. Most of the universe is just space, just quiet, just a stillness so deep and so complete that we have no real comparison for it here on Earth. Think about the space between our sun and the nearest star. That star is Proxima Centauri, a small red star that we mentioned earlier. It is a little more than 4 light-years away. To feel what that distance means, try this. Imagine the sun as a small ball, about the size of a grapefruit, sitting on a table. On this scale, the Earth would be a tiny speck, about the size of a grain of sand, orbiting about 30 feet away. The outer planets would be small pebbles, scattered across a few city blocks. And the nearest star, Proxima Centauri, would be another grapefruit sitting about 2,500 miles away. That is roughly the distance from New York to Los Angeles. All of that space between the two grapefruits is just emptiness. A few stray atoms here and there, a little bit of dust, but mostly nothing, mostly silence, mostly the quiet. Now multiply that distance by 100 billion, because there are roughly that many stars in our galaxy, and the galaxy is 100,000 light-years across. The distances between stars are not all the same, of course. In the dense center of the galaxy, stars are packed closer together. In the sparse outer arms, where our sun lives, they are spread much further apart. But even in the densest regions, stars are still separated by distances that make our solar system look small. And between the galaxies, the distances are larger still. The nearest large galaxy to our own, Andromeda, is about 2.5 million light-years away. That is 25 times the width of our entire galaxy. Just empty space, just quiet. So when we talk about the universe, we are really talking about emptiness. We are talking about a void so vast that the solid matter we think of as important, the stars, the planets, the dust clouds, is almost nothing in comparison. If you could shrink the whole observable universe down to the size of a large sports stadium, all the stars and planets and galaxies would be smaller than grains of pollen drifting in the empty air. The rest would be space, just space. But this emptiness is not something to fear. It is not a void in the sense of something missing. It is simply the natural state of things. The universe, by its nature, is mostly empty, and that emptiness is peaceful. It is still. It does not threaten. It does not press in. It is just there, a vast open landscape through which light and gravity move at their own pace. And this emptiness has a quality that is hard to find here on Earth. It is silent. Not quiet in the way a library is quiet, or a forest at night, but genuinely, completely, permanently silent. There is no sound in space. None at all. Sound is something we are so used to that we rarely think about what it actually is. Sound is a vibration moving through a substance. When you speak, your vocal cords vibrate, and that vibration pushes against the air molecules next to them. Those molecules bump into the molecules next to them, and so on, in a wave that spreads outward until it reaches someone's ear. The ear picks up the vibration and translates it into what we hear as sound. But the key part of that process is the substance, the medium. Sound needs something to travel through. It needs molecules to bump into each other. On Earth, the air does this job. Underwater, sound travels through water, and it actually travels faster and further there because water is denser than air. Even solid rock can carry sound vibrations. But space has no air. It has no water. It has no solid substance stretching between the stars. It is a vacuum, a nearly perfect vacuum, and in a vacuum, there are no molecules to bump into each other. There is nothing to carry the vibration. So sound cannot travel, it simply cannot exist. If you were to stand in the middle of interstellar space, which you could not because you would need a spacesuit and air to breathe, but if you could, you would hear nothing, not a whisper, not a hum, not the faintest rustle. You could have a star exploding nearby, a supernova, one of the most violent events in the universe, and you would hear absolutely nothing. The light would reach you, blindingly bright. The shockwave of particles might eventually reach you, but there would be no sound, no rumble, no roar, just silence. Perfect, unbroken silence. This idea can feel strange at first. We are so used to sound being part of our world that imagining its total absence is difficult. But once you sit with it for a while, the silence of space becomes something beautiful. It is not an eerie silence. It is not a scary silence. It is a natural stillness. It is the way things are when there is nothing to carry a vibration. The universe, for all its activity, the burning stars, the swirling galaxies, the slow collapse of dust clouds, does all of it in complete quiet. The universe does not make noise. It just does what it does, without a sound, and has done so for billions of years. Think about that. Every star that has ever shone has done so in silence. Every planet that has ever formed has done so in silence. Every comet that has swung around its sun, every asteroid that has tumbled through the void, every galaxy that has slowly turned, all of it in silence. The universe is a silent film, playing out across the eons, and we are some of the only things in it that can make a sound. And even our sounds do not travel far. They bounce around in our thin atmosphere and fade. Beyond that, nothing. The silence stretches on forever. This silence is restful. It means that out there, in the vast spaces between the stars, there is nothing to disturb, nothing to interrupt, nothing to jar you awake. The silence is like a blanket, soft and deep and all-encompassing. When you lie here in your bed, in the quiet of the night, you are getting just a small taste of what most of the universe is like all the time. The hush of a sleeping house is about as close as we can come to the silence of space. And even that is full of tiny sounds, the creak of floorboards, the hum of a refrigerator, the distant rustle of wind outside. True silence, the silence of interstellar space, is something we can only imagine. So let yourself imagine it now. Picture yourself floating in the space between stars. Not in a spaceship, not in a suit, just your awareness, drifting. There is nothing around you for light years in every direction, no planets, no asteroids, no dust, just the blackness and the distant points of light that are the stars. And there is no sound, no vibration, no pressure wave reaching your ears, just a stillness so complete that it feels almost like a presence of absence, a quiet that is not empty but full of peace, full of calm, full of the slow, steady passage of time. Now let's talk about what is actually in that empty space, because it is not completely empty. It is nearly empty, but not perfectly so. The space between the stars, what astronomers call the interstellar medium, contains a very thin scattering of gas and dust. The key word is thin. On average, in the space between stars in our galaxy, there is about 1 atom per cubic centimeter. Let that number settle. 1 atom. A cubic centimeter is about the size of a sugar cube. In a sugar cube of interstellar space, there is, on average, 1 single atom. Compare that to the air you are breathing right now. The air around you, at sea level, contains about 10 quintillion atoms per cubic centimeter. That is a 10 with 19 zeros after it, an enormous number. The air is thick with atoms, all jostling and bumping and carrying sound and heat and pressure. Interstellar space has 1 atom, just 1, occasionally 2 or 3, occasionally in slightly denser patches, a few dozen, but mostly just 1, a single lonely atom drifting through a volume that, on Earth, would be packed with more atoms than you could count in 1,000 lifetimes. That is how empty space is. The vacuum of interstellar space is a far better vacuum than anything we can create in a laboratory on Earth. We can pump the air out of a chamber, but even our best vacuum chambers still contain millions of atoms per cubic centimeter. Space has 1, maybe less. The emptiness is almost perfect. And that 1 atom is usually hydrogen. Hydrogen is the simplest atom, the lightest, the most common. It is the basic building block of the universe. Most of the normal matter in the cosmos is hydrogen. So the thin gas between the stars is mostly hydrogen, with a little helium mixed in and very tiny traces of heavier elements. The dust is even more sparse, tiny grains of solid material, mostly carbon and silicon and oxygen, formed in the atmospheres of old stars and blown out into space when those stars died. These dust grains are incredibly small, much smaller than the width of a human hair, and they are scattered so thinly that you could fly through a dust cloud for millions of miles and never hit a single grain. But over vast distances, that thin gas and dust adds up. It is enough to dim and redden the light of distant stars. It is enough to form new stars, when gravity pulls it together. It is enough to create the beautiful clouds we call nebulae, which we will visit later. But on a local scale, on the scale of a human body or a spaceship, it is almost nothing, almost a perfect vacuum, almost a perfect silence. And this vacuum has no temperature in the way we normally think of it. Temperature is a measure of how fast atoms are moving. In a near-perfect vacuum, there are almost no atoms to measure, so space itself does not have a temperature. An object in space, a spaceship, a rock, a person, would eventually reach a balance between the heat it absorbs from starlight and the heat it radiates away into the void. In deep interstellar space, far from any star, that balance point is very cold, just a few degrees above absolute zero. But the space itself is neither hot nor cold. It just is. It is a void that allows heat to pass through it without holding on to it. All of this, the emptiness, the silence, the cold, can sound harsh, but it is not. It is simply the natural condition of the cosmos. And for us, tonight, it is a reason to feel peaceful. The universe is not crowded. It is not noisy. It is not pressing in on us. It is vast and open and still. The stars are far apart. The galaxies are far apart. Everything has room to move, room to be, room to drift in its own quiet orbit without disturbance. Even within our own solar system, the space between planets is vast. The distance from the Earth to Mars varies, but on average it is about 140 million miles. That is so much empty space, so much silence. Our robotic probes cross that distance in months, and for most of that journey they are in the same deep quiet that fills the rest of the universe. They send back their signals, and the signals travel at the speed of light, taking minutes or hours to reach us. And in between, there is nothing. just the void, just the stillness. So when you feel the quiet of your room at night, when the world outside has gone still and the sounds of the day have faded, you are touching something real. You are touching the natural state of the universe. The silence you hear, or do not hear, is the same silence that fills the space between stars. It is the background condition of reality. Sound is the exception, silence is the rule. And this silence is not an absence, it is not a lack, it is a presence. It is the presence of space itself, vast and open and patient. It has been there since the beginning. It will be there at the end. It asks nothing of you. It does not need to be filled. It is already complete in its emptiness. There is a kind of comfort in that. We spend so much of our lives surrounded by noise, the noise of cities, of traffic, of conversations, of our own thoughts. We rarely get to experience true quiet. But out there, beyond the atmosphere, beyond the solar system, beyond the galaxy, the quiet is waiting. It has always been waiting. It is the most common thing in the universe, and we are just small creatures, living briefly on a small planet, surrounded for a little while by the rare luxury of sound. Let that thought settle. The silence of space is not something to be afraid of. It is something to rest in. It is the deep, calm breath of the cosmos. It is the long pause between the notes of the music. And we are here, in this moment, suspended in that silence, held by it, cradled by it. The stars are out there, burning quietly in the void. The galaxies are turning, slowly and without a sound. And you are lying here, eyes closed, breathing softly, a part of it all. The emptiness of space also means that things last. With no air, no water, no weather, there is nothing to erode or wear away. The footprints on the moon will last for millions of years. The craters on Mercury will stay sharp-edged for eons. The dust grains drifting between stars will drift essentially unchanged for the entire history of the universe. The quiet preserves things. It holds them in a kind of timeless embrace. We will talk more about this when we visit the moon next, but for now, just know that the stillness out there is not just empty. It is gentle, it is patient, it does not disturb. So as you drift here, between wakefulness and sleep, let yourself feel the quiet. Not the quiet of your room, exactly, but the quiet behind it, the deep quiet that stretches out in all directions, through the roof, through the atmosphere, into the space beyond. It is all around you. It has always been all around you. You are resting inside it, like a small seed resting in a vast, still field. And now, from that still field, we will turn our attention to something closer, something familiar. The moon, our nearest neighbor, the quiet companion that has circled the earth for billions of years, pulling gently on the oceans, lighting the night with reflected sunlight. We will visit it next, and see it not as a distant object, but as a place, a real place, with a surface and a history and a slow, patient orbit. The silence will come with us. The emptiness will come with us. But for now, just rest in the quiet between things. Let it hold you, softly, as you drift a little further down. The quiet holds you, and now we turn towards something closer, something you have seen many times, something that hangs in the night sky like a pale, familiar face, looking down on the earth with a steadiness that stretches back before memory, before history, before humans ever walked on two legs. The moon. The moon is our nearest neighbor. In a universe of vast distances, of light years and empty gulfs, the moon sits just a short step away, about 238,000 miles on average. That is not a large number in cosmic terms. It is close enough that the light from the moon takes just over 1 second to reach us, a little more than a second. If you stand outside on a clear night and look up at the moon, you are seeing it as it was 1¼ seconds ago. Not millions of years, not thousands, not even 8 minutes, like the sun, just 1 second. The moon is so close that the time delay barely registers. It is practically in our backyard. And yet, for all its closeness, The moon is a world of its own. It is not just a light in the sky, it is a place. A real, solid place with mountains and plains and craters and dust. If you could stand on its surface, you would feel the ground beneath your feet, just as you feel the ground here. You would look up and see the earth hanging in the black sky, a blue and white marble far larger than the moon ever looks from here. And all around you would be silence. The deep, perfect silence we talked about earlier, because the moon has no air to carry sound. It has no atmosphere at all. Let's think about that silence for a moment. On Earth, sound is always with us. Even in the quietest places, there is the rustle of wind, the distant call of a bird, the faint hum of the planet itself. But on the moon, there is none of that. If you were standing on the lunar surface and a boulder tumbled down a nearby hill, you would not hear it. You would see the movement, the slow slide of rock and dust, but it would happen in absolute quiet, like watching a film with the sound turned off. The vibrations would travel through the ground, through the rock, and you might feel them through your boots. But the air would carry nothing, because there is no air. The moon has no atmosphere to speak of. It has what scientists call a very thin exosphere, a scattering of atoms so sparse that it barely counts as an atmosphere at all. The Earth's air, thick and rich with oxygen and nitrogen, presses down on us with a weight we never notice because we have always lived with it. The moon has none of that pressure. Its surface is exposed directly to the vacuum of space. No wind, no weather, no clouds, no rain, no erosion in the way we know it here. And that has a remarkable consequence. The surface of the moon keeps records. It holds onto marks and scars for immense stretches of time. A footprint pressed into the lunar dust will stay there for millions of years. Not because the dust is special, but because there is nothing to erase it. No wind to blow it away. No rain to wash it smooth. No plants to grow over it. No animals to disturb it. Just stillness. Just the slow, patient silence of a world without weather. When the Apollo astronauts walked on the moon, they left footprints behind. Those footprints are still there today. They have been there for more than 50 years, and they will be there for millions of years more, barring some rare impact from a meteorite. The tracks of their rovers are still there. The places where they knelt to pick up rocks, where they planted scientific instruments, where they paused to look up at the earth, all of it remains, preserved in the quiet. The moon does not forget, it does not erase, it just holds onto everything, gently, in its timeless way. The craters on the moon tell the same story. Look at the moon through binoculars or a small telescope, and you will see them. Circles within circles, overlapping, some sharp-edged and fresh, others worn down by later impacts. But even the worn ones are not worn by wind or water. They are worn only by the slow rain of other impacts over billions of years. The moon has been sitting there, in its orbit, getting hit by rocks from space, and each hit leaves a mark that stays. The largest dark patches, the ones that form the face of the man in the moon, are ancient lava plains called Maria. They formed billions of years ago when volcanic activity flooded huge basins with dark basalt, and then the volcanism stopped and the lava cooled, and nothing much has happened to those plains since. They have just sat there, in the quiet, for 3 billion years or more. The moon is old. It formed about 4.5 billion years ago, around the same time as the Earth, from the debris of a giant collision between the young Earth and a Mars-sized body. That collision threw material into orbit, and that material gradually came together, under its own gravity, to form the moon. For a long time, the moon was much closer to the Earth than it is now. It loomed large in the sky, pulling enormous tides, its surface still hot and volcanic. But over the eons, it has been drifting away. The moon is still drifting away. It is moving away from the Earth at a rate of about 1.5 inches per year. That is not fast. It is slower than your fingernails grow. But it is steady. Every year, the distance between the Earth and the moon increases by the width of a few fingers. Over 1 million years, that adds up to about 15 miles. Over 1 billion years, it adds up to a noticeable change. The moon we see today is smaller in the sky than the moon the dinosaurs saw. And the moon that future creatures will see, millions of years from now, will be smaller still. Eventually, in the very far future, the moon will drift far enough away that total solar eclipses will no longer be possible. The moon will be too small in the sky to cover the sun completely. But that is a long, long way off. For now, the moon is still close enough to cover the sun just right. A coincidence of size and distance that makes our eclipses possible. The moon's drift is caused by tides. The moon's gravity pulls on the Earth's oceans, creating the familiar rise and fall of tides. But the Earth also pulls on the moon. The Earth's rotation is faster than the moon's orbit, and the tidal bulge of the oceans gets dragged ahead of the moon slightly. This tug gives the moon a tiny push, adding energy to its orbit, causing it to spiral outward ever so slowly. At the same time, the Earth's rotation is slowing down, very gradually, by a tiny fraction of a second per century. It is a slow dance between the two worlds, a transfer of energy that has been going on for billions of years and will continue for billions more. And there is another quiet detail about the moon's motion. The same side of the moon always faces the Earth. We call this the near side. The far side, sometimes misnamed the dark side, is turned away from us, and we never see it from the ground. This is not because the moon does not rotate. It does rotate. It spins on its axis. But its rotation period exactly matches its orbital period around the Earth. It takes the moon about 27 days to complete one rotation, and about 27 days to complete one orbit. So the same face stays pointed toward us at all times. This is called tidal locking, and it is a common phenomenon in the solar system. Many moons are tidally locked to their planets. It happens because the gravitational pull of the larger body creates friction that slows the smaller body's rotation over time until the two periods match. The far side of the moon looks different from the near side. It has fewer of the dark maria, the lava plains, and more craters. It is more rugged, more heavily scarred. For most of human history, no one had ever seen it. It was only in 1959 that a Soviet spacecraft, Luna 3, sent back the first blurry images of the far side. And it was only in 1968 that human eyes, the crew of Apollo 8, saw it directly from orbit. Now we have mapped it in detail with orbiting probes, and we know its contours as well as we know the near side. But it still holds a certain quiet mystery, simply because it is turned away from us. The light we see from the moon is not its own. The moon does not make light. It is not a star. It is a cold, dark rock, like the Earth in many ways, but without the internal heat that drives our planet's geology. The light we see is reflected sunlight. Sunlight hits the lunar surface and bounces off, and some of it bounces toward Earth. The brightness of the moon depends on its phase. When the moon is full, the sun is directly behind us, shining straight onto the moon's face, and the reflection is bright enough to cast shadows on Earth. When the moon is a thin crescent, the sun is off to the side, and most of the light is scattered away from us. The cycle of phases, from new to crescent to quarter to gibbous to full and back again, is caused by the changing angle between the sun, the moon, and the Earth. It is a slow, predictable rhythm, one that has been marking time for life on Earth since long before there were calendars. The moon's surface is covered in a layer of fine gray dust called regolith. It is the product of billions of years of impacts. Meteorites, large and small, have been hitting the moon for its entire history, pulverizing the rock into a fine powder. This dust is sharp and abrasive. It clings to everything, because there is no moisture to weigh it down, and it carries a faint electric charge from the solar wind. The Apollo astronauts found that it got into everything: their suits, their equipment, even the seals of the sample containers. It smelled faintly of gunpowder when they brought it back into the lander, a chemical reaction from the exposure to oxygen. But on the surface, in the vacuum, it has no smell at all. No smell, no sound, no wind. Just the gray dust stretching out in all directions, under a black sky that is forever. The temperatures on the moon are extreme, because there is no atmosphere to moderate them. In the direct sunlight, the surface can heat up to about 250 degrees Fahrenheit, hot enough to boil water. In the shade, or during the long lunar night, the temperature can drop to around minus 280 degrees Fahrenheit. That is cold enough to freeze almost anything solid. The moon's day and night cycle is slow. One lunar day, from sunrise to sunrise, lasts about 29.5 Earth days. So the sun hangs in the sky for about 2 weeks, and then the darkness lasts for another 2 weeks. Any machine or person on the surface has to survive both extremes, or find a way to insulate against them. And yet, despite these extremes, the moon is a place of great stillness. It is not a hostile place in the sense of being dangerous in an active way. It is just indifferent. It does not try to harm. It does not try to help. It simply is. Its surface bears the marks of violence from long ago, impacts that would have shattered whole regions, but that violence is in the past. The moon we see now is quiet. It has been quiet for billions of years. Its volcanoes are dead. Its interior has cooled. The only changes come from the occasional new impact, a flash of light and a fresh crater, and even those are rare. This stillness makes the moon a kind of anchor in our sky. It is the same moon that our ancestors looked at, the same phases, the same face, the same soft, reflected light falling on the earth at night. The moon has watched over the entire history of life on this planet. It has seen the first microbes stir in the oceans. It has seen the first plants creep onto the land. It has seen the dinosaurs rise and fall. It has seen the first humans look up and wonder what it was. And it has seen all of it in silence, from its slow orbit, pulling the tides, reflecting the light, asking nothing in return. When you lie here in the dark, the moon may be outside your window. It may not be. It may be new, invisible in the sun's glare. It may be full, washing the landscape in pale silver light. But even if you cannot see it, it is there. It is always there, circling the earth, held by gravity, drifting away by 1.5 inches a year. Its light is touching the top of the atmosphere, filtering down through the air, landing softly on rooftops and trees and quiet streets. And if you were to go outside and look up, you would see the same moon that has been seen by every generation of humans, and by many creatures before them, stretching back into the deep time of the earth. The moon is a reminder that not everything in the universe is far away and strange. Some things are close, some things are familiar, some things have been with us for so long that we almost forget how remarkable they are. The moon is a world in its own right, but it is also a companion, a quiet neighbor, a pale lamp in the night that asks nothing of us and gives only light. And so we leave the moon now, still drifting in its slow orbit, still holding its footprints and craters in perfect silence. We turn our attention to the source of the light that illuminates it, the sun, the star that makes all of this possible, the slow, steady furnace that has been burning for 4.5 billion years and will burn for billions more. But that is for the next part of our journey. For now, just picture the moon hanging in the dark, pale and peaceful, its light just over a second old, its surface still and silent under the endless sky. Let that image settle in your mind, calm and constant, as you drift a little further into stillness. The moon hangs in the dark, pale and peaceful, and the light that makes it glow is now our focus. That light comes from the sun. The sun is the reason we are here. It is the reason the earth is warm enough for liquid water. It is the reason plants grow, why winds blow, why the sky is blue during the day. It is the anchor of our solar system, the great steady presence around which everything else turns. And it is a star, just one star among many. But to us, it is the star, the one that matters most. The sun is an enormous ball of mostly hydrogen and helium, held together by its own gravity. It is so large that it contains more than 99% of all the mass in the entire solar system. All the planets, all the moons, all the asteroids and comets and dust, All of that combined is less than 1% of what the Sun holds. Jupiter, the largest planet, is about 1,000th the mass of the Sun. The Earth is about 1/300,000th the mass. We are tiny in comparison. The Sun's diameter is about 109 times wider than the Earth's. If the Sun were a hollow ball, you could fit about 1.3 million Earths inside it. That is hard to picture, and you do not need to try. Just know that the Sun is vast. It dominates our little corner of space. And the Sun is not solid. It is a sphere of hot, glowing gas, what scientists call plasma. Plasma is a state of matter where the atoms are so hot that the electrons are stripped away, leaving a soup of charged particles. The Sun is plasma all the way through, from its core to its visible surface. There is no solid ground to stand on. If you could somehow fall into the Sun, you would sink into it, through layers of increasing density, until you were crushed and dissolved long before reaching the center. But we are not going into the Sun tonight. We are just going to think about it from here, from our safe distance of about 93 million miles. That distance, 93 million miles, is what astronomers call one astronomical unit. It is a convenient measure for distances within our solar system, and as we talked about earlier, light from the Sun takes about 8 minutes to cross that gap. 8 minutes. The sunlight that warms your skin on a summer afternoon, that filters through leaves, that sparkles on the surface of a lake, that light is 8 minutes old by the time it reaches you. It was born deep inside the Sun, thousands of years before that, but its journey through space, from the solar surface to the Earth, takes just 8 minutes. Not long, in the grand scheme of things, but still a delay, still a reminder that even the closest star is far enough away that light takes measurable time to travel. And the Sun is a star. It is easy to forget that, because it looks so different from the other stars. The other stars are tiny points of light, faint and distant. The Sun is a blazing disk that fills the daytime sky with brightness. But the only difference is distance. The Sun is close, the other stars are far away. If you could take the Sun and move it to the distance of the nearest star, it would look just like a star, a bright one certainly, but just a point of light twinkling in the night. And if you could take that nearest star, Proxima Centauri, and bring it as close as the Sun, it would be fainter and redder, but it would still dominate the sky, still warm a planet, still be the center of a solar system. The Sun is a star, a very ordinary star in many ways. Not the biggest, not the hottest, not the brightest, just a middle-aged, medium-sized star in the prime of its life. The Sun is roughly 4.5 billion years old. That number again, 4.5 billion. It formed from a collapsing cloud of gas and dust, much like the nebulae we will visit later. Gravity pulled the material together, and as the cloud shrank, it heated up. At the center, the temperature and pressure rose until they reached a critical point. At that point, hydrogen atoms began to fuse together into helium. This process, called nuclear fusion, releases enormous amounts of energy, and that energy is what makes the Sun shine. Nuclear fusion is the slow, steady burning at the heart of every star. It is not like a fire on Earth, which is a chemical reaction. Fusion is a nuclear reaction, taking place at the level of the atom's core. In the Sun's center, the temperature is about 15 million degrees Celsius, and the pressure is immense, more than 200 billion times the pressure of Earth's atmosphere at sea level. Under those conditions, hydrogen nuclei, which are single protons, slam into each other with enough force to overcome their natural repulsion and stick together. Through a series of steps, 4 hydrogen nuclei combine to form one helium nucleus, and in that process, a tiny amount of mass is converted into energy, according to the famous equation, energy equals mass times the speed of light squared. That is a lot of energy from a tiny bit of mass. The Sun converts about 600 million tons of hydrogen into helium every second. 600 million tons every second. And it has been doing this for 4.5 billion years. Despite that enormous consumption, the Sun still has plenty of fuel. It is roughly halfway through its main life. It has enough hydrogen in its core to keep fusing for about another 5 billion years. 5 billion more years of steady burning. That is longer than the Earth has existed so far. So there is no hurry, no urgency. The sun will keep shining, steadily and reliably, for a span of time that is almost impossible to grasp. Long after we are gone, long after our children and their children and every trace of our civilization has vanished, the sun will still be there, doing what it does, burning hydrogen in the quiet of space. The energy produced in the sun's core does not instantly reach the surface. It takes a very long time. The core is incredibly dense, and the photons, the particles of light, cannot travel in a straight line. They bounce around, absorbed and re-emitted by the dense plasma, taking a random walk toward the surface. It can take a single photon tens of thousands of years, sometimes hundreds of thousands of years, to make its way from the core to the surface. The light we see today was generated in the core long before modern humans existed. Once the photons reach the surface, called the photosphere, they escape into space and travel the 8 minutes to Earth in a straight line. But their journey began in the deep interior, in the slow, patient heart of the sun, ages ago. The surface of the sun, the photosphere, is about 5,500 degrees Celsius. That is hot enough to melt any material we know of. Above the photosphere is the chromosphere, a thinner layer of gas that glows with a reddish color, and above that is the corona, the sun's outer atmosphere, which extends millions of miles into space. The corona is very thin, but it is also very hot, millions of degrees, for reasons that are not fully understood. It is visible during total solar eclipses as a pearly white halo around the dark disk of the moon. The corona is also the source of the solar wind, a stream of charged particles that flows outward through the solar system, past the planets, past the outer planets, out to the very edge of the sun's influence. The solar wind is gentle but persistent. It shapes the tails of comets, pushing them away from the sun. It interacts with Earth's magnetic field, creating the auroras, the northern and southern lights. And it creates a protective bubble around our solar system called the heliosphere, which shields us from some of the high-energy particles coming from the rest of the galaxy. The sun, in its quiet way, looks after us. It provides light and warmth and a shield against the wider cosmos. The sun also has a rhythm. It goes through a cycle of activity that lasts about 11 years. During the peak of the cycle, the sun has more sunspots, dark patches on the surface that are slightly cooler than the surrounding area. Sunspots are caused by intense magnetic activity. They come and go, sometimes growing large enough to be visible from Earth with proper eye protection. During the quiet part of the cycle, sunspots are few. Then they build again. This 11-year pulse has been going on for as long as we have been observing the sun, and almost certainly for much longer. It is a heartbeat of sorts, a slow, steady rhythm that marks the sun's magnetic life. The sun rotates, but not as a solid body, because it is a ball of plasma. Different parts rotate at different speeds. The equator rotates faster than the poles. This differential rotation twists and tangles the sun's magnetic field, which is what drives the sunspot cycle and the occasional solar flares. Solar flares are bursts of energy and particles that can affect satellites and power grids on Earth, but even these are not violent in the grand scheme of things. They are just the sun stretching its magnetic limbs, releasing a little tension, and settling back down. And the sun is only one of many. Our galaxy, the Milky Way, contains an estimated 100 billion stars or more. Some estimates go as high as 400 billion. The sun is one of them. It is not special, it is not unique. It is a very average star in a very large collection of stars. But to us, it is everything. It is the source of all the energy that powers our world. The food we eat, the fuel we burn, the wind that turns the turbines. All of it traces back to the sun. Even the atoms in our bodies were forged in earlier generations of stars. Stars that lived and died before the sun was born. The sun is our parent star, the current keeper of our warmth and light. In the far future, the sun will change. It will not burn steadily forever. In about 5 billion years, the hydrogen in its core will run low. The core will contract and heat up, and the outer layers will expand. The sun will become a red giant star, swelling to perhaps 200 times its current size. It may swallow Mercury and Venus, and perhaps the Earth as well. Even if the Earth survives, its surface will be scorched and sterilized. The oceans will boil away. The atmosphere will be stripped off. The world we know will be gone. But that is a very long time from now. That is 5 billion years. More time than the Earth has existed so far. There is no need to worry about it. It is just the natural life cycle of a star like the sun. It will happen quietly and inevitably in the deep future, and after the red giant phase, the sun will shed its outer layers, creating a brief, beautiful cloud of gas called a planetary nebula. The core will remain, a small, dense, hot ball of carbon and oxygen called a white dwarf. That white dwarf will slowly cool over billions and billions of years, fading from white to yellow to orange to red, and eventually, after unimaginable spans of time, to a cold, dark lump of crystallized carbon. In a way, the sun's core will become a diamond, the size of the Earth, floating silently in the space where our solar system used to be. But all of that is in the far, far future. For now, the sun is in its middle age, steady and warm and reliable. It rises every morning and sets every evening. It pours its light down on the earth, feeding the plants, warming the soil, driving the weather. It is the great constant of our lives, even though we know, in the back of our minds, that it is not truly constant. It is just steady on human timescales. On cosmic timescales, it is a brief flare of light, a temporary gathering of energy and matter, here for a while and then gone. But a while in cosmic terms is very long indeed. Long enough for life to arise and evolve and wonder about it. Long enough for us to be here, tonight, thinking about it as we drift towards sleep. So let the sun rest in your mind now. Picture it out there, beyond the dark side of the earth, shining steadily in the void. Its light is streaming out in all directions, only a tiny fraction of it hitting our planet, the rest pouring out into space, toward the other planets, toward the outer solar system, toward the stars. Some of that light will travel for years, decades, centuries, millennia, before it reaches anything at all. Some of it will never hit anything. It will just keep going, crossing the vast emptiness between the stars, forever. The sun does not know we are here. It does not know anything. It is just a star, doing what stars do, burning its fuel in the quiet of space. And we are here, on this small planet, in its warm embrace, for a little while. That is enough. We will leave the sun now and turn our attention outward, to the larger structure that contains it, the Milky Way, our galaxy, a vast, spinning collection of stars and gas and dust, 100 billion suns or more, all moving together through the void. That is the next part of our journey, but for now, just rest in the steady warmth of the idea of the sun, a slow, steady furnace in the dark, burning quietly, asking nothing, giving everything. Hold that image gently as you drift a little further down toward rest. The sun rests in the mind now, a steady warmth in the dark, and we turn our attention outward, to the larger structure that contains it, the Milky Way, our galaxy, a vast, spinning collection of stars and gas and dust, 100 billion suns or more, all moving together through the void. The sun is one of those stars. Our Earth is one tiny world orbiting that one star, and the whole system, the sun and its planets and all the asteroids and comets, sits inside this much larger thing, this great wheeling disk of light and matter that we call home. The Milky Way is a spiral galaxy. That means it is shaped roughly like a flattened pinwheel, with curling arms winding out from a bright center. If you could float above it and look down, you would see a structure of great beauty, a central bulge of older, yellower stars, a flat disk stretching out from that bulge with graceful spiral arms winding through it. The arms are traced by young, hot blue stars and by the glowing clouds of gas where new stars are being born. The whole thing is embedded in a larger, fainter halo of old stars and dark matter, but the disk is the part we can see most easily. We cannot float above it, of course. We are inside it. We are embedded in the disk, about halfway out from the center, in one of the spiral arms. That arm has a name. It is called the Orion arm, or sometimes the Orion spur, because it is a smaller branch off a larger arm. Our sun and all the stars we see in the night sky are part of this arm. When we look up at the Milky Way, that pale, cloudy band that stretches across a dark sky, we are looking along the plane of the disk. We are seeing the combined light of millions of stars too distant and too faint to make out individually. Their light blurs together into a soft, milky glow. That is where the name comes from, the Milky Way. The ancient Greeks called it the Galaxias, from their word for milk, and that is where we get the word galaxy. On a clear, dark night, far from city lights, the Milky Way is one of the most beautiful sights in nature. It stretches from horizon to horizon, a river of faint light with darker patches running through it. Those dark patches are not empty, they are clouds of dust, immense veils of material that block the light of the stars behind them. The dust is made of tiny grains of carbon and silicon, expelled by old stars and drifting in the space between. It obscures our view of the galactic center, which is why we cannot see the bright core of our galaxy with our naked eyes. The center is there, hidden behind curtains of dust. If the dust were not there, the galactic center would be one of the brightest things in the night sky. The Milky Way is enormous. Its disk is about 100,000 light-years across. That means light from a star on one edge of the galaxy takes 100,000 years to reach a star on the opposite edge, and the galaxy contains a huge number of stars. The exact number is hard to pin down, because most of the stars are faint and far away, and many are hidden by dust. But astronomers estimate that the Milky Way contains somewhere between 100 billion and 400 billion stars. Let that number sit for a moment. 100 billion. That is a 1 followed by 11 zeros. If you tried to count them, 1 per second, it would take you more than 3,000 years. And that is the low estimate. The high estimate is 4 times that. Each of those stars is a sun. Some are larger and hotter than our sun. Some are smaller and cooler. Some are in binary pairs, 2 stars orbiting each other. Some are in larger clusters, groups of dozens or hundreds or thousands of stars, born together from the same cloud of gas. Many of them, we now know, have planets. The number of planets in the galaxy is probably even larger than the number of stars. Trillions of worlds, of all sizes and temperatures, orbiting their parent stars in the quiet of the disk. Our sun sits about 26,000 light-years from the galactic center. That is a bit less than halfway out to the edge. We are in the suburbs, not the downtown. The inner parts of the galaxy, closer to the center, are more crowded with stars. They are also more active, with more radiation and more frequent stellar explosions. Out here, in the spiral arm, things are calmer. The distances between stars are larger. The pace of life is slower. It is a good place for a quiet solar system to form and persist for billions of years. The entire galaxy is rotating. Everything in it is moving. The stars orbit the galactic center, just as the planets orbit the sun. But because the galaxy is not a solid object, different parts move at different speeds. The inner parts rotate faster than the outer parts. The sun, at its distance, takes about 220 million years to complete one full orbit around the galactic center. This period is sometimes called a cosmic year or a galactic year. 1 galactic year ago, the dinosaurs were beginning their reign on Earth. The continents were in different positions, the atmosphere was different, and the sun was in a different part of its orbit, with different stars around it. In 1 galactic year, the sun travels roughly 550 million miles around the center. That sounds fast, and it is. The sun is moving at about 500,000 miles per hour relative to the galactic center. But because the distances are so vast, It still takes 220 million years to complete the loop. The Earth, of course, goes along with the Sun. So do all the other planets. We are all moving together, a tiny fleet of worlds, on this slow, majestic journey around the hub of the galaxy. And the galaxy itself is moving through space. It is not stationary, it is part of a small cluster of galaxies called the local group. The local group contains the Milky Way, the Andromeda Galaxy, and about 50 or so smaller galaxies. All of these galaxies are moving relative to each other, held together by their mutual gravity. The Milky Way and Andromeda are the two largest members of the group, and they are slowly falling toward each other. In about 4 billion years, they will begin to merge, their stars mingling, their structures distorting, eventually forming a new, larger galaxy. But that is far in the future, and we will talk more about it when we come to the expanding universe. At the center of the Milky Way, there is a black hole. It is called Sagittarius A star, and it has a mass of about 4 million times that of the Sun. It sits at the very heart of the galaxy, surrounded by a dense cluster of old stars and hot gas. This black hole is not actively feeding at the moment. It is relatively quiet, but its gravity dominates the inner region, and stars can be seen orbiting it at tremendous speeds. We will talk more about black holes later. For now, just know that one sits at the center of our galaxy, a dark anchor around which everything turns. The Milky Way is not just a collection of stars. It is also full of gas and dust. The gas is mostly hydrogen, the raw material for making new stars. The dust is the heavier material, the carbon and silicon and oxygen, formed in the cores of earlier stars and scattered into space when those stars died. This gas and dust drifts in the spaces between the stars, sometimes thin and diffuse, sometimes gathered into dense clouds. These clouds are the nurseries where new stars are born. We will visit one of those nurseries next. For now, just picture the galaxy as a great, living system, with stars being born in the spiral arms, living their lives, and dying, returning their material to the gas and dust, which will someday form new stars. It is a slow cycle, a cosmic ecology, that has been going on for billions of years. The Milky Way is old. The oldest stars in the galaxy are nearly as old as the universe itself, about 13 billion years. The galaxy formed from the collapse of a large cloud of gas and dark matter in the early universe. Over time, it grew by pulling in smaller galaxies and merging with them. This process still continues. The Milky Way is currently pulling apart several small dwarf galaxies that are orbiting too close, their stars being stretched into long streams that wrap around our galaxy. These streams are faint, but they can be detected by careful observation. They are the remnants of ancient collisions, the scars of a long and patient history. When you lie here in the dark, the Milky Way may be overhead. If it is a clear night and you are far from city lights, you could go outside and see it. A pale band stretching across the sky, made of the light of 100 billion distant suns. Some of those suns are like our own. Some are larger and brighter. Some are smaller and fainter. Some have planets. Some do not. Some are just being born. Some are dying. All of them are so far away that their light has taken years, or centuries, or millennia to reach your eyes. And yet there they are, visible on a dark night, a reminder of the scale of things. The Milky Way has been seen by every generation of humans who lived before electric lights. Our ancestors looked up at it and told stories about it. Some saw a river, some saw a road, some saw the spilled milk of a goddess. The name has stuck across languages and cultures because the sight is so striking. A band of light, soft and diffuse, arcing across the sky. It is the disk of our galaxy, seen from the inside. We cannot step outside to get a different view. This is the view we have, and it is a beautiful one. And even if you cannot see it tonight, even if you live in a city where the lights wash out the sky, it is still there. It is still above you, behind the glow, behind the buildings, behind the clouds. The stars are still shining. The disk is still turning. The sun is still carrying us on its long orbit. The galaxy does not care if we see it or not. It just does what it does, in its slow and patient way. There is comfort in that. The Milky Way has been here for most of the history of the universe. It will be here for a long time to come, even as it changes and merges and evolves. And we are part of it. We are made of its material, born from its cycles of star death and star birth. The iron in your blood, the calcium in your bones, the oxygen in your breath, all of it was forged in the cores of stars that lived and died in this galaxy long before the sun was born. You are not separate from the Milky Way. You are a piece of it, a small, thinking piece, lying here in the dark, drifting toward sleep. So let the image of the galaxy settle in your mind, a great spiral of stars turning slowly, silently, in the vastness of space. The sun is a tiny dot in one of its arms. The earth is a smaller dot around that dot, and you are here, on the surface of that dot, held by gravity, breathing the air, resting in the quiet. The galaxy does not ask for your attention, but it is there, all around you, in every direction. You are inside it. You have always been inside it, and it has always been turning, slow and steady, carrying you along. We will move next to the places within the galaxy where stars are born. The nebulae, the slow nurseries of stars. These are the clouds of gas and dust that dot the spiral arms, glowing faintly in the dark, gathering material, collapsing under gravity, and quietly, patiently, giving birth to new suns. But for now, just rest with the Milky Way. Picture its pale band stretching across a dark sky. Picture the countless stars within it, each one a sun, each one a story, and let that vast, calm image carry you a little deeper into stillness. The vast, calm image of the Milky Way lingers, and now we drift into one of its quiet corners. A place where stars are born, not in a flash of light or a sudden burst of energy, but slowly, gradually, patiently, over spans of time so long that a human lifetime passes in the blink of an eye by comparison. These places are called nebulae. Nebulae are the slow nurseries of stars. The word nebula comes from the Latin word for cloud, and that is exactly what a nebula is, a cloud. A great, drifting cloud of gas and dust, hanging in the space between the stars. Some nebulae are small and dense. Some are vast and diffuse, stretching across dozens or hundreds of light years. They are made mostly of hydrogen, the simplest and most common element in the universe, with some helium mixed in, and a tiny sprinkling of heavier elements, carbon, oxygen, nitrogen, and others. The dust is made of tiny solid grains, smaller than particles of smoke, composed of silicates and carbon compounds. These grains are the raw material for making planets, but that comes later. First, the cloud must give birth to a star. Nebulae form from the material cast off by older stars. When a star like the Sun nears the end of its life, it puffs off its outer layers, sending gas and dust drifting out into space. When a much more massive star dies, it explodes, scattering its material even more widely. Over time, this material mixes with the thin gas already in the galaxy, and gravity begins to do its slow work. The material gathers, it clumps, it forms denser regions within the larger cloud. And in those dense regions, the process of star formation begins. It starts in complete darkness. The dense pockets of a nebula are cold and opaque. They block visible light. If you could float just outside one of these pockets, you would see a dark, inky blob silhouetted against the fainter glow of the nebula behind it. These dark patches are called Bok globules, named after the astronomer who studied them. Inside them, the temperature is just a few degrees above absolute zero. The atoms are moving slowly. The dust grains are coated with thin layers of ice. It is quiet. It is still. And yet, in that stillness, something is happening. Gravity is pulling. Every particle in the cloud pulls on every other particle. The force is tiny, almost too small to imagine, but the cloud is enormous, and there are a lot of particles, and they have a very long time to work. Over hundreds of thousands of years, the densest parts of the cloud begin to contract. They shrink under their own weight. As they shrink, they spin up, just a little, like water going down a drain. The material near the center falls inward. The material further out flattens into a rotating disk, and at the very center, a dense knot of gas is growing hotter and hotter. This is how a star begins. Not with a bang, but with a slow inward fall. The gravitational energy of the collapsing material is converted into heat. The core of the protostar, that is the word for a star in the process of forming, gets hotter and denser. At first, it glows only in the infrared, a warm ember hidden inside its dusty cocoon. But over time, as more material piles on, the temperature and pressure at the center rise to extraordinary levels. When the core temperature reaches about 10 million degrees Celsius, something profound happens. The hydrogen atoms begin to fuse. The same process we described in the sun's core, nuclear fusion, switches on. 4 hydrogen nuclei press together to form one helium nucleus, releasing a burst of energy. The star ignites. It begins to shine. The outward pressure from the fusion energy pushes back against the inward pull of gravity, and the star stabilizes. It has become a true star, a self-sustaining ball of plasma, and it will shine for millions or billions of years to come. This entire process, from the initial contraction of the cloud to the ignition of fusion, takes hundreds of thousands of years for a star like the Sun. For smaller stars, it can take even longer. For larger stars, it can happen more quickly, in just a few 100,000 years. But even that is a very long time by human standards. There is no rush, no urgency. The cloud has been drifting for millions of years already. It can wait. And as the new star begins to shine, it illuminates the surrounding nebula. The gas and dust glow with reflected starlight. The hot young stars also emit ultraviolet radiation, which excites the hydrogen gas, causing it to glow with a characteristic pinkish-red color. This is why many nebulae appear red in telescope images. They are not burning, they are fluorescing, like a neon sign, lit up by the energy of the newborn stars embedded within them. The leftover material in the rotating disk around the star does not go to waste. It is the stuff from which planets form. The dust grains in the disk begin to stick together, forming larger and larger clumps. Over millions of years, these clumps grow into planetesimals, and then into protoplanets, and eventually into full-fledged worlds. The star and its planets form together, from the same cloud, at the same time. Our own solar system began this way, in a nebula that has long since dispersed. One of the most famous stellar nurseries in our sky is the Orion Nebula. It is visible to the naked eye on a clear, dark night, a faint smudge in the constellation Orion, just below the 3 stars of Orion's belt. Through a telescope, it is a glorious sight, a glowing cloud of gas and dust, lit up by a cluster of young, hot stars at its center. Those stars are only a few million years old, which is very young for stars. They are still embedded in the cloud from which they formed. Around them, new stars are still being born. The Orion Nebula is about 1,300 light-years away, which in cosmic terms is not far. It is one of the closest regions of active star formation to Earth. The Orion Nebula is just one of many such places in the galaxy. There are nebulae in every spiral arm. The Eagle Nebula, with its famous Pillars of Creation, is another. The Carina Nebula, a vast and complex region of star formation in the southern sky. The Lagoon Nebula, the Trifid Nebula, the Rosette Nebula. Each one is a nursery, a quiet place where gravity and time work together to turn diffuse gas into concentrated sunlight. These nebulae are not permanent. They are transient structures in the life of the galaxy. A nebula exists for a few tens of millions of years at most. The young stars that form within it eventually blow away the remaining gas and dust with their radiation and stellar winds. The nebula disperses, its material spread out into the galaxy, where it may someday become part of another nebula and form another generation of stars. The cycle continues. The galaxy recycles its material, over and over, across billions of years. The nebula that gave birth to our sun and our solar system is long gone. It dispersed more than 4.5 billion years ago. But the material that made it did not vanish. Some of it became the sun, some of it became the earth and the other planets, some of it became the water in our oceans, the carbon in our bodies, the oxygen in our air, and some of it drifted away, back into the galaxy, where it may have become part of other stars, other planets, other life. We are connected, through our atoms, to the nebulae of the distant past. There is something deeply restful about nebulae. They are clouds. They drift. They do not hurry. The processes within them unfold over timescales that make a human life seem like a fleeting moment. And yet, without them, we would not be here. Every star in the sky, every planet, every living thing, traces its origin back to a cloud of gas and dust, slowly collapsing under its own weight in the quiet of the galaxy. Picture a nebula now. Picture a great, glowing cloud, soft-edged and luminous, hanging in the dark of space. Its colors are faint, pale pinks and blues, wisps of darker dust threading through it. At its heart, a cluster of young stars is shining, their light just now escaping the cloud after a journey of thousands of years. Around them, the remaining gas is being sculpted into pillars and ridges and delicate tendrils by the pressure of starlight. New stars are still forming in the densest knots. Protostars, still hidden in their dusty cocoons, are growing warmer by the century. And all of this is happening in perfect silence. No sound. No fanfare, just the slow, patient work of gravity and time. A nebula does not know it is beautiful. It does not know it is a nursery. It is just a cloud, doing what clouds do. But we can look at it, from our vantage point on this small planet, and see in it the story of our own beginning. The atoms in your body were once part of a nebula. They drifted in space for millions of years. They gathered together. They became part of the earth. And now they are part of you, lying here in the dark, listening to these words. The connection is real. It is not poetry. It is physics. The calcium in your bones, the iron in your blood, the sodium and potassium that allow your nerves to fire, all of it was forged in stars and scattered by nebulae. You are made of the stuff of the cosmos, and the nebulae are where that stuff was gathered and shaped. This process is still going on. Right now, at this very moment, in some spiral arm of the Milky Way, a cloud of gas is beginning its slow collapse. A new star is forming, its core heating up, its fusion soon to ignite. Planets are coalescing from the disk around it. Few million years, a new solar system will be shining, and the nebula that gave it birth will be dispersing. The cycle continues. It has continued for most of the history of the universe. It will continue for a long time yet. There is no end to this process, only transformation. The gas becomes stars. The stars shine for a while. Then they die, returning their material to the galaxy. That material becomes new nebulae. The nebulae give birth to new stars. It is a cycle without beginning and without end, a slow breathing of the galaxy, in and out over eons. And we are part of that breath. We are here for just one small moment of it, a brief flicker of awareness in a universe that has been making stars for more than 13 billion years. That thought could feel small, but it does not have to. It can feel peaceful. It can feel like belonging. You are not separate from the nebulae. You are the nebulae, grown dense and warm and aware, looking back at the sky from which you came. So let the image of a nebula settle in your mind, a soft, glowing cloud in the dark, a quiet nursery, a place where stars are born, slowly and without hurry. The Orion Nebula is up there right now, faint and smudgy to the naked eye, a place of deep cold and hidden warmth. You can find it, if you ever want to, just below the belt of Orion, but you do not need to find it tonight. You can just hold the idea of it, a cloud of gas and dust drifting in the spiral arm, giving birth to stars in its own time. And those stars, once born, will live their lives. each one different, each one unique. Some will be small and cool and red. Some will be large and hot and blue. Some will live alone, some will live in pairs or groups. The variety of stars in our galaxy is vast, and we will visit some of them next. The other stars, the ones that are not our sun, the ones that are quietly different, quietly themselves, burning in the dark. But for now, rest with the nebulae, the slow clouds, the quiet nurseries. Let their patient, timeless work remind you that there is no hurry, not out there, and not in here. Everything in its own time, everything drifting, slowly, toward its own becoming. Everything drifting, slowly, toward its own becoming. And now we drift toward those other stars, the ones that are not our sun, the ones that fill the galaxy in their countless numbers, each one a sun in its own right, each one with its own story, its own character, its own quiet way of burning in the dark. We have spent time with our sun. We have learned that it is a star, a ball of hot plasma, steadily fusing hydrogen into helium, giving off light and warmth. And we have said that the sun is ordinary, a middle-sized, middle-aged star, not particularly remarkable in any way. But that does not mean all stars are like the sun. In fact, stars vary enormously. They come in a wide range of sizes and colors and temperatures. Some are so small and dim that you could not see them from Earth without a telescope, even though they are among the closest stars to us. Some are so large and bright that they outshine the sun by hundreds of thousands of times. The galaxy is full of variety, and tonight we are going to meet some of these other stars, quietly and without hurry. The most common type of star in the galaxy is not like the sun at all. The most common type is the red dwarf. Red dwarfs are smaller than the sun, cooler than the sun, and much dimmer than the sun. Their surfaces glow with a reddish-orange light, which is why they are called red. They are not actually red in the way a stop sign is red. They are more of a warm orange, but the name has stuck. Red dwarfs make up roughly 70 to 80% of all the stars in the Milky Way. If you were to pick a star at random from the galaxy, odds are it would be a red dwarf. And yet, you cannot see a single red dwarf with your naked eye. Not one. They are too dim. The closest star to our solar system, Proxima Centauri, is a red dwarf. It is just over 4 light-years away, but it is so faint that you need a telescope to spot it. If you could stand on a planet orbiting Proxima Centauri and look back at the sun would be a bright star in the sky. But from Earth, Proxima is invisible without instruments. That is how dim red dwarfs are. But what red dwarfs lack in brightness, they make up for in patience. They burn their fuel very slowly. A star like the sun will last for about 10 billion years in its main phase. A red dwarf, because it is smaller and cooler, uses its hydrogen much more sparingly. The smallest red dwarfs can continue fusing hydrogen for trillions of years. Trillions. That is hundreds of times longer than the current age of the universe. Not a single red dwarf in the entire universe has yet reached the end of its life. They are all still in their infancy, still burning quietly, still with almost all of their fuel ahead of them. If you could stand on a planet orbiting a red dwarf, the sky would look different. The star would hang large and dim, perhaps several times the apparent size of the sun in our sky, but glowing with a warm orange light. The shadows would be softer. The colors of the landscape would be muted. If the planet were close enough to be warm, it might be tidally locked, with one side always facing the star and the other always in darkness. That would create a very different world from ours. But we are not visiting such a world tonight. We are just picturing the star itself, small and steady, burning its fuel with a patience that is almost impossible to grasp. At the other end of the scale are the giant stars. Stars much larger than the sun, much hotter and much brighter. These stars are rare, but they dominate the night sky because they are so luminous. The brightest stars you can see, Sirius, Vega, Rigel, are all more massive than the sun. They burn fiercely, pouring out energy at a tremendous rate, and because they burn so fiercely, they live short lives. A star 10 times the mass of the Sun might last only a few tens of millions of years. A star 50 times the mass of the Sun might last only a few million. That sounds long, but in cosmic terms it is a mere flicker. These massive stars live fast and die young, and when they die spectacularly. But that is a story for later. The color of a star tells you its temperature. This is one of the simplest and most beautiful facts in astronomy. A cooler star glows red, a hotter star glows orange or yellow, a still hotter star glows white. The hottest stars glow blue-white, or even blue. This is the same principle that makes a piece of metal glow red when it is heated, then orange, then white. Stars are the same. Their color is a direct indicator of their surface temperature. Our Sun is a yellow star, with a surface temperature of about 5,500 degrees Celsius. It is in the middle of the range. Red dwarfs have surface temperatures of 2,500 to 4,000 degrees. Blue giant stars can have surface temperatures of 30,000 degrees or more. They are so hot that most of their light is in the ultraviolet, invisible to our eyes, but what we do see is a brilliant blue-white. These colors are subtle to the naked eye. Most stars look white or slightly yellowish, because our eyes are not sensitive enough to pick up the faint tints in dim light. But through a telescope, or in long-exposure photographs, the colors become vivid. A star field is not just a scatter of white points, it is a garden of colors: red, orange, yellow, white, blue. Each one a different temperature, each one a different mass, each one at a different stage of its life. Some stars do not live alone. Many stars are members of binary or multiple systems. 2 stars, or 3, or sometimes more, orbiting each other in a slow gravitational dance. In fact, it is estimated that more than half of all stars are in binary systems. Our Sun, with its single companionless state, may be in the minority. Binary stars can be beautiful to think about. Imagine a planet with 2 suns in the sky. One large and orange perhaps, the other smaller and white. They would rise and set at different times, casting double shadows, painting the landscape in shifting colors. Sometimes one sun would eclipse the other, creating a dimmer, stranger light. The orbital dance of 2 stars around their common center of mass is a quiet, steady thing, governed by the same gravity that holds the moon around the Earth. It lasts for millions or billions of years, unchanging, reliable. Some binary stars are so close together that they almost touch. Their gravity distorts them, pulling them into egg shapes, and material can flow from one star to the other. Some are so far apart that they take thousands of years to complete a single orbit. In all cases, they are bound together, partners in the long journey through the galaxy. Then there are the variable stars. Stars whose brightness changes over time. Some vary because they are pulsating, expanding and contracting in a regular rhythm, like a slow heartbeat. Cepheid variable stars, named after the prototype Delta Cephei, are particularly important. Their pulsation period is directly linked to their true brightness, which makes them valuable tools for measuring distances across the galaxy and beyond. By watching how fast a Cepheid pulses, astronomers can determine how bright it really is, and by comparing that to how bright it appears from Earth, they can calculate how far away it must be. It is a quiet, elegant piece of cosmic measurement, built into the stars themselves. Other variable stars change brightness because they are eclipsing binaries, 2 stars whose orbital plane is aligned with our line of sight, so that one passes in front of the other, dimming the combined light. This too is a slow, regular rhythm, a clockwork of shadow and light, playing out across the light years. And then there are the truly enormous stars, the red giants and red supergiants. These are stars that have exhausted the hydrogen in their cores and have swollen to vast sizes. They are in the late stages of their lives, and they are immense beyond easy comprehension. One of the most famous is Betelgeuse. Betelgeuse is the reddish star that marks the shoulder of the constellation Orion. It is a red supergiant, roughly 550 light-years away, though the exact distance is hard to pin down. What we do know is that Betelgeuse is enormous. If you were to take Betelgeuse and place it where the Sun is, its outer surface would extend past the orbit of Mars. It would swallow Mercury. It would swallow Venus. It would swallow Earth. It would swallow Mars. Jupiter might be safe, but everything inward of it would be inside the star. Think about that for a moment. A single star, large enough to contain the entire inner solar system. And yet Betelgeuse is not even the largest star known. There are stars like UY Scuti and Stephenson 218 that are even larger, though their exact sizes are uncertain. These stars are so vast that if you could fly around them in an airplane, it would take thousands of years to complete one circuit. Their outer layers are thin and diffuse, barely more than a warm vacuum, but they are part of the star nonetheless. Betelgeuse is also a variable star. Its brightness fluctuates over periods of months and years. A few years ago, it dimmed noticeably, and there was speculation that it might be about to go supernova, to explode. That would be a sight to see. A star in our own galaxy, visible in the night sky, suddenly flaring to the brightness of the full moon, casting shadows at midnight. But Betelgeuse did not explode. It returned to its normal brightness. It is still there, in Orion, glowing reddish and faint, biding its time. It will explode someday, that is certain. But someday, in cosmic terms, could mean tomorrow, or it could mean 100,000 years from now. There is no hurry. When a massive star like Betelgeuse does finally explode, it will be the end of a long story. The core of the star will collapse, and the outer layers will be blasted into space, scattering heavy elements, carbon, oxygen, silicon, iron, across the galaxy. Those elements will enrich future nebulae, future stars, future planets. The death of a massive star is the birth of new material. The cycle continues. Smaller stars, like the Sun, end their lives more gently. They do not explode. They swell into red giants, puff off their outer layers into a planetary nebula, and leave behind a white dwarf, a dense, hot core that slowly cools over billions of years. The white dwarf is about the size of Earth, but with the mass of a star. A teaspoon of white dwarf material would weigh tons. It is matter compressed to an extreme degree, electrons packed so tightly that they resist further collapse only through a quantum mechanical effect called electron degeneracy pressure. That is a complicated phrase, and you do not need to remember it. Just know that white dwarfs are strange, dense objects, the remnants of once bright stars, slowly fading in the dark. The variety of stars in the galaxy is a reminder that the universe is not uniform. It is not all the same. There are patterns and categories, but within those categories there is endless variation. Every star is a little different from every other star. Slightly more mass, slightly less. Slightly hotter, slightly cooler. A different age, a different composition, a different companion, or none at all. The galaxy is like a vast garden, filled with flowers of different colors and sizes, each one growing at its own pace, blooming in its own time. And yet, all these stars are made of the same basic stuff, hydrogen and helium mostly, with traces of heavier elements. They are all governed by the same laws of physics, gravity, pressure, nuclear fusion. The same equations describe a red dwarf and a blue supergiant. The differences are just a matter of scale, a matter of mass. A little more gravity here, a little more heat there, and the star takes on a completely different character. It is a quiet demonstration of how variety can emerge from simplicity. The stars we see in the night sky are just a tiny sample of what is out there. On a clear, dark night, far from city lights, the human eye can see about 2,500 stars at any one time. 2,500. That sounds like a lot, but it is only the closest, brightest stars. It is a tiny fraction of the 100 billion or more stars in the Milky Way, and the Milky Way is just one galaxy among hundreds of billions in the observable universe. The number of stars in the universe is larger than the number of grains of sand on every beach on Earth. We mentioned that earlier. It is a number so large that it loses meaning, but it is also a number that is true. It is a fact about the universe we live in. And in all that vastness, We have not yet found another star that hosts life. We have found planets, many planets, thousands of confirmed planets around other stars, with many more candidates waiting to be verified. Some of those planets are rocky, like Earth. Some are in the habitable zone of their stars, where temperatures could allow liquid water. But we do not yet know if any of them harbor life. We do not yet know if we are alone. That is one of the great unanswered questions, and it is okay not to know the answer. The universe is under no obligation to tell us. It keeps its own counsel. It has been keeping it for billions of years, and it will keep it for billions more. So we drift now among the other stars, not our sun, but its cousins, the red dwarfs, burning patiently for trillions of years, the blue giants, blazing fiercely and briefly, the yellow stars like our own, steady and warm, the binaries, dancing in their slow orbits, the variables pulsing with their quiet rhythms, the supergiants, vast and diffuse, nearing the end of their lives. All of them are out there, right now, shining in the dark, each one a story, each one a quiet flame in the void. Picture a red dwarf, small and cool and steady. Its light is faint, but it will still be shining long after the sun has died, long after the Earth is gone, long after the Milky Way has merged with Andromeda and formed a new galaxy. That little red star will still be there, burning its hydrogen one atom at a time, in no hurry at all. It is a kind of anchor in the future, a promise of persistence. The universe will be a darker place in the far, far future, when the massive stars have all died and only the red dwarfs remain. But it will still be full of stars, faint red stars, scattered across the galaxies, shining for trillions of years. The universe still has most of its life ahead of it. Let that thought settle. The universe is not old and fading, it is still young. The era of stars has only just begun. The red dwarfs are just getting started. The galaxies are still forming and merging. There is so much time ahead, so much quiet unfolding still to come. And we are here at the beginning of that long, slow story, seeing only the first few chapters. And now we will turn from the stars themselves to the planets that orbit some of them. Our own solar system has a family of planets, and we will visit the outer ones next, the gas giants. Saturn with its rings, Jupiter with its great storm, cold, slow-moving worlds that circle the sun at vast distances. But for now, just rest with the stars, the many kinds of stars, each one different, each one quiet, each one burning in the dark, asking nothing, giving only light. Let that image fill your mind as you drift a little further into the calm. The stars rest in the mind now, each one a quiet flame in the dark. And we turn inward from those distant suns, back toward our own solar system. Not to the inner planets, the rocky worlds close to the sun, but to the outer ones, the giants, the cold, slow-moving worlds that circle the sun at vast distances. Jupiter and Saturn, Uranus and Neptune. These are the planets that dominate the outer solar system, and tonight we are going to spend some time with them, especially Saturn, especially its rings. Saturn is the sixth planet from the Sun. It is a gas giant, like Jupiter, meaning it has no solid surface to stand on. It is made mostly of hydrogen and helium, the same elements that make up the Sun and most of the universe. Deep inside Saturn there is probably a rocky core, surrounded by layers of metallic hydrogen and then an outer envelope of gas. But if you were to descend into Saturn's atmosphere, you would never find a place to land. The gas would just get thicker and thicker, the pressure higher and higher, until you were crushed long before reaching anything solid. Saturn is about 9.5 times wider than Earth. It is the second largest planet in the solar system after Jupiter. It orbits the Sun at a distance of roughly 890 million miles, nearly 10 times farther than Earth. At that distance, the Sun looks much smaller in the sky. Sunlight at Saturn is only about 1% as bright as it is at Earth. The planet is cold and dim, bathed in a perpetual twilight by our standards. A year on Saturn, the time it takes to complete one orbit around the Sun, lasts about 29 Earth years. Saturn moves slowly. There is no hurry out there. But Saturn is not famous for its size or its distance. Saturn is famous for its rings. The rings of Saturn are one of the most beautiful sights in the solar system. Through a telescope, even a small one, they are stunning. A flat, bright disk of material encircling the planet, with gaps and divisions that give it structure. The rings look solid from a distance, like a vinyl record or a wide brim hat, but they are not solid. They are made of countless small pieces of ice and rock. The particles in Saturn's rings range in size from tiny grains, no larger than dust, to chunks as big as a house. Most of them are made of water ice, with some rocky material mixed in. They are spread out across a vast area, but they are extremely thin. The rings span about 175,000 miles across, but in most places they are only about 30 feet thick. 30 feet. If you could shrink the rings down to the size of a sheet of paper, they would be thousands of times thinner than the paper itself. They are a vast, delicate structure, a whisper of material stretched across the void. The rings are not one uniform disk. They are divided into distinct bands, separated by gaps. The largest gap, called the Cassini division, is wide enough to be seen from Earth with a modest telescope. It separates the bright A ring from the broader B ring. Closer to Saturn, there is the faint, dusky C ring. Farther out, there are the narrow F ring and the diffuse E ring, among others. Each ring has its own character, its own density, its own pattern of particles. The rings are a complex system, shaped by gravity and by the subtle influence of Saturn's moons. The origin of the rings is not known for certain. They may be the remains of a moon that was torn apart by Saturn's gravity. Or they may be leftover material from the formation of the planet itself, material that never coalesced into a moon. Or they may be the debris of a moon that was shattered by a collision. Whatever their origin, the rings are not permanent. They are slowly being eroded. Particles from the rings are raining down into Saturn's atmosphere, a phenomenon called ring rain. In another 100 million years or so, the rings may be gone. That sounds like a long time, and it is, but it means that we are lucky to be alive in the era when Saturn has its rings. We are seeing the planet at a special time in its history. Imagine floating just above the rings. They would stretch out in front of you like a vast, flat plain of glittering ice. The particles closest to you would be visible as individual chunks, slowly tumbling in their orbits. Further away, they would blur together into a bright band. The sun would be a distant point of light, casting long shadows. Saturn itself would loom overhead, a pale golden globe, banded with faint stripes of cloud. And all of it would be silent, perfectly silent. The ring particles would bump and jostle and grind, but in the vacuum of space, you would hear none of it. Just the quiet, just the still, cold beauty of an outer planet. Saturn has many moons. More than 140 are known, and there are probably more that are too small to detect from Earth. The largest is Titan. Titan is a remarkable world in its own right. It is larger than the planet Mercury, and it is the only moon in the solar system with a thick atmosphere. That atmosphere is mostly nitrogen, like Earth's, but with methane and other hydrocarbons mixed in. The surface of Titan is hidden beneath a layer of orange haze, but radar and infrared instruments have revealed a landscape of lakes and rivers. Not lakes of water, it is much too cold for liquid water on Titan's surface. The lakes are made of liquid methane and ethane. Titan has a weather cycle, with methane rain and methane clouds, much like Earth's water cycle but with different chemistry. It is a strange, cold, but strangely familiar world. Another of Saturn's moons, Enceladus, is much smaller, only about 300 miles across, but it has captured the attention of scientists because it spews plumes of water vapor and ice from its south pole. These plumes come from a global ocean of liquid water beneath the moon's icy crust. The water is salty, and it contains organic molecules. Enceladus is one of the places in the solar system where life might possibly exist, in the dark, warm waters beneath the ice. We do not know if it does. That remains an open question, and one we may not answer for a long time. But tonight, we are not searching for life. We are just visiting, just drifting through the outer solar system, looking at the sights. And there is another giant to visit, Jupiter. Jupiter is the largest planet in the solar system. It is more than 11 times wider than Earth, and it has more mass than all the other planets combined. It is so large that its gravity affects the orbits of the other planets, and it acts as a kind of shield for the inner solar system, deflecting or capturing many of the comets and asteroids that might otherwise come our way. Jupiter is made mostly of hydrogen and helium, like the Sun, but it is not massive enough to ignite fusion in its core. If it were about 80 times more massive, it would be a star, and our solar system would have 2 suns. But it is not. It is a planet, the king of planets, dominating the outer reaches. Jupiter has bands of clouds that wrap around it in alternating stripes of light and dark. These bands are created by the planet's rapid rotation. Jupiter spins once in just under 10 hours, so fast that it bulges noticeably at the equator. The bands are made of different chemicals at different altitudes, which give them their colors. Ammonia, sulfur, phosphorus compounds. These trace substances tint the clouds in shades of white, tan, brown, and orange. The bands are stable over long periods, but they shift and change slowly, a quiet weather system on a scale that is hard to comprehend. And within those bands, there is a storm that has been raging for centuries. The Great Red Spot. The Great Red Spot is a giant, oval-shaped storm, larger than the Earth. It has been observed continuously since at least the year 1831, and it was probably seen even earlier. That means it has been churning for at least 150 years, and likely much longer. It is a high-pressure system, spinning counterclockwise, with winds reaching hundreds of miles per hour. And yet, it is slowly shrinking. When the Voyager spacecraft flew by in the 1970s, the Great Red Spot was about twice the size of Earth. Now it is a little over 1 Earth across. In time, it may fade away entirely. But for now, it is still there, a red eye staring out from the face of the giant. Jupiter also has rings, but they are faint and dark, nothing like Saturn's. They were discovered by the Voyager spacecraft in 1979. They are made of dust, probably knocked off Jupiter's moons by impacts. They are so faint that they cannot be seen from Earth without a telescope, and even then, only under ideal conditions. And Jupiter has moons. Many moons. 4 of them are large enough to be worlds in their own right. These are the Galilean moons, named after Galileo, who first saw them through his telescope in 1610. Io, Europa, Ganymede, and Callisto. Io is the most volcanic body in the solar system. Its surface is constantly being resurfaced by eruptions of molten sulfur. It is pulled and squeezed by the gravity of Jupiter and the other large moons, creating tidal heating that melts its interior. Europa is an ice-covered world with a global ocean of liquid water beneath the ice. Like Enceladus, it is a candidate for possible life. Ganymede is the largest moon in the solar system, larger than Mercury. Callisto is a heavily cratered, ancient surface, one of the oldest landscapes in the solar system. Each of these moons has its own story, its own quiet character, orbiting the giant planet in their slow, steady paths. Beyond Jupiter and Saturn lie the ice giants, Uranus and Neptune. These are smaller than Jupiter and Saturn, but still much larger than Earth. They are made of water, ammonia, and methane ices, mixed with hydrogen and helium. Their blue colors come from methane in their atmospheres, which absorbs red light and reflects blue. Uranus is tilted on its side, probably from a giant collision early in its history. Its rings and moons orbit it in a plane that is almost perpendicular to the plane of the solar system. Neptune has the strongest winds in the solar system, reaching speeds of more than 1,000 miles per hour, even though it receives very little energy from the distant sun. These outer planets are cold. The temperature at the cloud tops is hundreds of degrees below 0 Fahrenheit. They are far from the sun's warmth, and they receive only a tiny fraction of the light that we do. Their orbits are slow. Uranus takes 84 Earth years to circle the Sun. Neptune takes 165. A year on Neptune is longer than a human lifetime. The pace of time out there is different. Slower, more stretched out. The seasons change over decades, not months. The Sun is just a bright star in the sky, not a disk. And yet, even out there, the planets are still held by the Sun's gravity, still part of the same solar system, still quietly doing what they have done for billions of years. There is a restful quality to the outer planets. They are far away, they are slow, they are cold and quiet. They do not demand attention. They have been circling the Sun for 4.5 billion years, and they will keep circling for billions more. Their storms may rage, their moons may crack and shift, but on the scale of the solar system, they are steady. They are permanent features of our cosmic neighborhood. Think of Saturn now. Picture its pale golden globe, wrapped in its delicate rings. The rings are tilted, catching the distant sunlight, glowing faintly. They are made of ice, countless trillions of tiny ice particles, each one following its own orbit, each one part of a larger structure that is beautiful and fragile and temporary. The rings are there tonight, as they were last night, as they will be tomorrow night. They are there whether anyone is looking or not. They have been there for millions of years, and they will be there for millions more, slowly raining down into the planet, slowly thinning, slowly fading. There is no need to see them. Just knowing they are there is enough. And picture Jupiter, its bands of cloud, its great red spot, its family of moons. Imagine standing on the surface of Europa, looking up at the giant planet hanging in the sky. It would be enormous, filling a large part of the sky, its stripes and storms visible to the naked eye. The ice beneath your feet would be cracked and ridged, glowing faintly in the dim sunlight. Somewhere below, in the dark ocean, there might be something alive, or there might not. The silence would not tell you either way. The outer planets are a reminder that our solar system is larger than we tend to think. We focus on Earth, on the inner planets, on the Sun. But there is so much more out there. The solar system extends far beyond the orbit of Neptune, into the Kuiper Belt and the Oort cloud, regions of icy bodies and dwarf planets. Pluto is out there, a small, cold world with mountains of ice and a thin atmosphere that freezes and thaws with its long seasons. There are other dwarf planets, Eris, Haumea, Makemake. There are comets that swing in from the outer darkness, trailing their tails of gas and dust. The solar system is a vast and complex place, and we have only touched on a small part of it tonight. But that is enough. We do not need to cover everything. We are just drifting, just visiting, just letting the images pass through the mind like clouds across a dark sky. The outer planets are out there, right now, in their slow orbits. Saturn's rings are shining, Jupiter's storm is churning, Neptune's winds are blowing. And all of it is happening in silence, in the cold, in the dark, without any need for an audience. Let that sense of distance and quiet settle over you. The outer solar system is a peaceful place. It is far from the noise and heat of the inner worlds. It is a place of slow time and faint light. It asks nothing of you. It just is. And now, from these cold outer planets, we will turn to something even stranger, something that lurks in the dark of the galaxy. Black holes. Places where gravity is so strong that nothing, not even light, can escape. But that is for the next part of our journey. For now, just rest with Saturn and its rings. Picture them in the dark of the outer solar system, pale and beautiful and silent, drifting slowly around the Sun. Let that image be the last thing in your mind as you sink a little deeper into the calm. The image of Saturn fades, pale and silent, and we drift now towards something stranger, something that lurks in the dark of the galaxy, in the centers of galaxies, in the places where gravity has won its quiet victory over everything else. Black holes. A black hole is a place where gravity is so strong that nothing, not even light, can escape. That is the simplest definition. It is a region of space where matter has been packed so tightly that the force of gravity overwhelms everything else. Once something crosses a certain boundary, it cannot come back. That boundary is called the event horizon. Beyond it, the universe as we know it simply stops. Black holes form when very massive stars reach the end of their lives. We talked earlier about how stars like the Sun end their lives gently, puffing off their outer layers and leaving behind a white dwarf. But a star that is much more massive than the Sun, say 20 or 30 times the mass, does not end gently. When such a star runs out of fuel, its core can no longer support itself against the inward pull of gravity. The core collapses. In a fraction of a second, an enormous amount of mass is squeezed into an incredibly small space. The outer layers of the star fall inward, then rebound in a tremendous explosion called a supernova. What is left behind, at the center, is the collapsed core. If the core is massive enough, it becomes a black hole. The collapse is so complete that the matter is crushed down to a point of infinite density. This point is called the singularity. We do not know what the singularity is like. The laws of physics as we understand them break down there. The numbers stop making sense. The singularity is hidden behind the event horizon, so we cannot observe it directly. We can only describe the region around it. The event horizon is not a physical surface. It is not a wall or a shell. It is simply the distance from the singularity at which the escape velocity equals the speed of light. Escape velocity is the speed you need to leave a gravitational field. On Earth, the escape velocity is about 7 miles per second. That is how fast a rocket must go to break free of Earth's gravity and reach space. On a black hole, the escape velocity at the event horizon is the speed of light, 186,000 miles per second. Since nothing can travel faster than light, nothing can escape from inside the event horizon. The event horizon is the point of no return. The size of the event horizon depends on the mass of the black hole. For a black hole with the mass of the Sun, the event horizon would be only about 3.5 miles across. For a black hole with 10 times the Sun's mass, the event horizon would be about 35 miles across. For the supermassive black hole at the center of our galaxy, which has a mass of about 4 million suns, the event horizon is about 14 million miles across, about 1/3 the distance from the Sun to Mercury. These are not large sizes by cosmic standards. Black holes pack a lot of mass into a very small space. And yet, despite their name, black holes are not cosmic vacuum cleaners. They do not suck in everything around them. This is a common misunderstanding. A black hole is just a mass, like any other mass, and its gravity works the same way. If the Sun were to be replaced by a black hole of exactly the same mass, the Earth and all the other planets would continue to orbit exactly as they do now. They would not be pulled in. The gravity at their distance would be the same. It would just be much darker and much colder. The black hole would not reach out and grab them. It would simply sit there, in the center, a dark sphere of warped space, while the planets circled around it as they always have. Objects can safely orbit a black hole as long as they stay outside the event horizon. The closer you get, the stronger the gravity becomes, and the faster you need to orbit to stay in a stable circle. There is an innermost stable circular orbit, inside of which any object would spiral inward. But as long as you stay outside that radius, you can orbit a black hole indefinitely. It is only if you cross the event horizon that you cannot return. What happens inside the event horizon is unknown. This is one of the great mysteries of science, and it is important to say that plainly. We do not know. Our current theories of physics cannot describe the interior of a black hole. General relativity, the theory of gravity developed by Albert Einstein, predicts the existence of the singularity, a point where density becomes infinite and the equations break down. But most physicists believe that the singularity is a sign that the theory is incomplete. A better theory, one that combines gravity with quantum mechanics, might describe what actually happens at the center. But we do not have that theory yet. We are still working on it. So we must sit with the not knowing. The inside of a black hole is one of the places where our understanding stops, and that is fine. That is part of the calm. The universe does not owe us answers. It keeps its secrets, and some of those secrets may remain for a very long time. There is a peacefulness in acknowledging that. We do not have to know everything. We can simply recognize the boundary between what we know and what we do not, and rest there. Black holes are not just theoretical. We have very good evidence that they exist. We have observed stars orbiting an invisible object at the center of our galaxy. Those stars move at tremendous speeds, tracing out elliptical orbits that can only be explained by a huge mass concentrated in a very small space. The invisible object is Sagittarius A star, the supermassive black hole at the center of the Milky Way. In 2019, astronomers using a network of radio telescopes around the world produced the first image of a black hole's shadow. The image showed the supermassive black hole at the center of a galaxy called M87, a ring of hot gas surrounding a dark central region, the shadow of the event horizon. It was a remarkable achievement, and it confirmed in a very direct way that black holes are real. Black holes come in different sizes. Stellar mass black holes, formed from the collapse of massive stars, have masses ranging from a few times the mass of the Sun to a few dozen times. Intermediate mass black holes, with masses of hundreds or thousands of suns, may exist but are harder to find. And supermassive black holes, with masses of millions or billions of suns, sit at the centers of most large galaxies. How these supermassive black holes formed is not fully understood. They may have grown from smaller black holes that merged and accumulated gas over cosmic time, or they may have formed directly from the collapse of enormous gas clouds in the early universe. The details are still being worked out. Black holes can also merge. When two black holes orbit each other closely, they lose energy through the emission of gravitational waves, ripples in the fabric of space-time itself. These ripples carry energy away, causing the black holes to spiral inward and eventually collide. The merger produces a burst of gravitational waves that can be detected by instruments on Earth. The first such detection was made in 2015, and since then, dozens of black hole mergers have been observed. These events happen in complete silence, far away in distant galaxies, and the waves they produce travel across the universe, stretching and squeezing space by tiny amounts as they pass through. Gravitational waves are a new way of observing the universe. They are not light. They are not sound. They are vibrations in the geometry of space itself. When a gravitational wave passes through you, and they do, all the time, from distant events, you are stretched and squeezed by an amount smaller than the width of an atomic nucleus. You do not feel it. You do not notice it. But the instruments can detect it. The universe is ringing quietly, with the echoes of ancient collisions, and we are just beginning to learn how to listen. Despite their extreme nature, black holes have a strange kind of stillness. Once they form, they are very simple objects. A black hole can be described completely by just three numbers: its mass, its electric charge, its spin, or angular momentum. That is all. There is no other information. The black hole does not care what fell into it. It does not remember the type of star it came from, or the planets it swallowed, or the gas it consumed. It is just mass, charge, and spin. Everything else is lost or hidden behind the event horizon. This simplicity is almost elegant. A black hole is the ultimate simplification of matter. It is gravity taken to its logical extreme. It is a place where the complexity of the universe is reduced to its bare essentials. And yet, inside that simplicity, there is mystery. The question of what happens to the information that falls into a black hole, the so-called information paradox, is one of the deepest puzzles in physics. We will not solve it tonight. We will just note that it exists and that it is okay not to have the answer. There is something calming about black holes if you approach them in the right way. They are not monsters. They are not threats. They are just objects, part of the natural universe, doing what gravity does. They sit in the centers of galaxies, anchoring the orbits of stars. They drift through the spiral arms, the remnants of long-dead massive stars. They merge and ring space like a bell, and all of it happens in silence, in the dark, without any need for our attention. If you could float near a black hole, at a safe distance, outside the event horizon, you would see something strange and beautiful. The black hole itself would be invisible, but the space around it would be distorted. The gravity of the black hole bends light, acting like a lens. You would see the stars behind the black hole appear to shift and stretch, their light curving around the dark center. If the black hole were surrounded by a disk of hot gas, you would see that gas glowing brightly, its light also bent into strange shapes. The disk would appear to wrap around the black hole, above and below, because the gravity bends the light from the far side of the disk up toward your eyes. It would be a vision of warped reality, silent and still. But you do not need to picture all of that. You can just hold the idea of a black hole gently in your mind. A dark, quiet place in space. A place where gravity is so strong that light itself cannot leave. A place where the universe as we know it comes to an edge. And beyond that edge we do not know what lies. The not knowing is part of the peace. The universe does not tell us everything. It keeps some things to itself, and that is fine. Some questions about black holes may simply stay unanswered for a long time. What is the singularity really like? What happens to the information that falls in? Is there a way to unify gravity and quantum mechanics that describes the interior? We do not know. We may not know for generations, and that is fine. The black holes do not care if we understand them. They just sit there, in the dark, doing what they do, as they have done for billions of years. So let the black hole rest in your mind now. Not as something frightening, but as something quiet. A dark well in space, a place of mystery, a reminder that the universe is not finished telling us its story, and it is in no hurry to finish. We can wait. We can rest here, in the calm, and let the mysteries be mysteries. There is no need to solve them tonight. There is no need to solve them ever. And now, from these dark wells of gravity, we will turn to the largest scale of all, the universe itself. The quiet expansion that has been going on since the beginning, the faint glow that fills all of space, the dark energy that pushes the galaxies apart. These are the last things we will visit tonight, before we begin our slow drift toward rest. But for now, let the black hole be a quiet presence in the back of your mind, a dark spot in the galaxy, a place where light goes to rest, and let that image carry you gently forward into the next part of the night,